At the center of every galaxy lies a monster. These are the 50 secrets of supermassive black holes, the invisible giants that rule the cosmos. By the end of this journey, you will understand how these enigmatic objects control the fate of galaxies and challenge the very laws of physics. We will uncover how they formed so quickly after the Big Bang and what happens to matter at the point of no return. What cosmic mystery captivates you the most? Their mass is almost beyond comprehension. Think of our Sun, a colossal sphere of incandescent gas so massive it holds our entire solar system in its gravitational embrace. Now picture not 1 but 4 million of our suns. That is the estimated mass of Sagittarius, a star, the supermassive black hole at the heart of our own Milky Way galaxy. And that is considered small. Some of these cosmic giants hold the mass of tens of billions of suns, all compressed into a region of space smaller than our solar system. This unimaginable density creates a gravitational pull so absolute that it dictates the motion of everything around it. Hundreds of billions of stars, swirling clouds of gas, and entire solar systems all dance to the silent tune of this central, invisible conductor. Their orbits are not random. They are a direct response to the black hole's overwhelming presence, a celestial map charting the influence of the unseen. To truly grasp this scale, consider our own cosmic neighborhood. The entire solar system, from the Sun out to the distant orbit of Neptune, would fit comfortably inside the event horizon of Sagittarius, a star. That is the point of no return, the boundary beyond which not even light can escape. Our whole world, every planet and every bit of space dust, would simply vanish inside that dark sphere. This is not just a matter of size, but of consequence. The sheer mass of a galaxy's central black hole is the fundamental reason it can shape its entire home. It controls the flow of gas that births new stars and can, with immense outbursts of energy, halt star formation entirely. But how do we weigh something we cannot see? Astronomers become cosmic detectives, watching the frantic dance of stars whipping around the galactic center. By precisely tracking the speed and path of these stars over many years, they can calculate the mass of the invisible object they are orbiting. It is like deducing the presence and weight of a giant by watching how a flock of birds swirls around it. That silent conductor, with a mass of 4 million suns, presents a profound mystery. How did something so immense come to exist? The formation of these supermassive black holes is a cosmic race against time. We observe them shining brightly in the infant universe, a mere few 100 million years after the Big Bang. This is not enough time for a typical black hole to grow so large by slowly feeding on gas. It is like finding a giant redwood tree sprouting in a field that was barren soil only a year before. Something extraordinary must have happened to create such massive seeds so quickly. One compelling theory is the direct collapse model. Imagine, in the early cosmos, a vast and pristine cloud of pure hydrogen and helium gas. This cloud does not fragment to form stars as it normally would. Instead, it remains stable, cool, and dark, collapsing under its own immense weight in one single catastrophic event. It bypasses starlight entirely, condensing directly into a black hole with a starting weight of tens of thousands of suns. This gargantuan seed is then primed for rapid growth, giving it a colossal head start. Another possibility points to the first generation of stars. These primordial giants, known as population 3 stars, were behemoths, hundreds of times more massive than our Sun. They lived fast and died young, exploding in supernova that left behind black hole seeds. While smaller than direct collapse seeds, these remnants could have quickly bulked up through 2 primary methods. The first is accretion, a steady diet of surrounding gas drawn in by their powerful gravity. The second is through violent mergers where smaller black holes collide and combine, building mass in sudden, dramatic leaps. Modern supercomputers now run simulations to test these ideas, creating virtual universes where these ancient processes play out. These digital laboratories, combined with new observations from the most powerful telescopes, are beginning to piece together this cosmic origin story. We are finally starting to understand how the universe built its first monsters in the darkness, setting the stage for everything that followed. This boundary of no return, the event horizon, is not a physical surface you could touch. It is a point of mathematical certainty in the fabric of space and time. Think of it as the edge of a cosmic waterfall. From a distance, space flows smoothly towards the black hole like a river. As you get closer, the current picks up speed. The event horizon is that final, invisible lip where the flow of space itself becomes faster than the speed of light. Cross that line and you are carried over the edge irrevocably, no matter how powerful your engines. It is crucial to distinguish this boundary from the black hole's true heart, the singularity. The event horizon is the point of no return, while the singularity is the final destination, a point of infinite density where all the collected mass is crushed into a volume of zero size. Our understanding of physics simply shatters there. The laws of gravity, as described by Einstein, predict this infinite point, but infinity is a concept that does not exist in the real world as far as we know. This conflict points to a deeper mystery, a place where our knowledge ends and true cosmic secrets begin. This leads to one of the most heated debates in theoretical physics, the information paradox. According to Einstein's work, information about anything that falls into a black hole should be lost forever, erased from our universe. But quantum mechanics, the rules governing the very small, insists that information can never be truly destroyed. It is the ultimate cosmic contradiction. One proposed and deeply unsettling solution is the firewall paradox. This idea suggests that the event horizon is not a smooth, empty space as traditionally thought. Instead, it might be a seething wall of unimaginably high energy, a literal firewall that would instantly incinerate any object crossing it. This resolves the information problem but creates another, violating Einstein's principle that someone falling into a black hole should not notice anything special as they cross the horizon. Physics as we know it breaks down at this threshold. For decades, the event horizon was a purely theoretical concept. Then, in April 2019, humanity was given its first visual evidence. The Event Horizon Telescope, a global network of observatories working in unison as a planet-sized dish, revealed the shadow of the supermassive black hole in the galaxy M87. That dark central void, encircled by a fiery ring of light, is not the event horizon itself, but its shadow cast against the glowing matter swirling around it. It is the closest we have ever come to seeing the unseeable, a direct silhouette of the point of no return. That first glimpse of the event horizon's shadow brings a terrifying question to mind. What would actually happen if you fell in? The answer is as bizarre as it is brutal, a process with a strangely culinary name, spaghettification. It begins with gravity's simple, unforgiving rule. The pull you feel from a black hole is not uniform. Your feet, if you fell in feet first, would be closer to the black hole than your head. Even a small difference in distance creates a vast difference in gravitational pull. The force on your feet would be exponentially stronger than the force on your head. You would be stretched lengthwise into a long, thin stream of atoms. Simultaneously, the sides of your body would be compressed inward by the same extreme forces, squeezing you from all directions. You would quite literally become a human strand of spaghetti, a single, elongated line of matter spiraling toward the void. This is the result of tidal forces, the same kind of gravitational stretching that the moon imposes on Earth's oceans to create tides, but amplified to an unimaginable, lethal extreme. The nature of this gruesome end depends entirely on the size of the monster you are confronting. For a stellar mass black hole, the kind formed from a collapsing star, the event horizon is very close to the central singularity. The change in gravity over that short distance is monstrously sharp. You would be spaghettified long before you even reach the point of no return, torn apart by the incredible gradient in the gravitational field. A supermassive black hole, however, is a different kind of beast. Because its mass is spread over such a vast volume, its event horizon is much farther out. The tidal forces at that boundary are far gentler, relatively speaking. You could theoretically cross the event horizon of a supermassive black hole completely unharmed, at least at first. You would not feel a sudden jolt or a dramatic tearing sensation. The pull of gravity would feel smooth and uniform across your body. This presents a chillingly serene hypothetical scenario. An astronaut in a spacecraft could cross the event horizon of a supermassive black hole like Sagittarius, a star, and for a brief window of time continue their doomed journey inward. They would be alive, conscious, and cut off from the entire universe forever, but the reprieve is only temporary. As they journeyed farther inward, the gravitational gradient would steadily increase. The difference in pull between their head and their feet would become noticeable, then uncomfortable, then unbearable. The stretching would begin, a slow and inexorable pull into a stream of particles. Their spacecraft would be similarly stretched and torn apart, atom from atom, joining the cosmic river of matter flowing toward the central singularity. This bizarre fact means that falling into a supermassive black hole offers a longer, more contemplative, and ultimately more terrifying descent into the unknown. This descent into a supermassive black hole, however terrifying, is a journey few would ever witness. To see the monster, you must look not at the darkness itself, but at the brilliant, swirling storm that surrounds it. This is the accretion disk, a cosmic maelstrom of gas and dust caught in the black hole's irresistible gravitational grip. Picture a vast whirlpool of water circling a drain, but this whirlpool is made of plasma heated to millions of degrees and glows with the fury of a billion stars. It is this disk, not the black hole, that produces the most brilliant light in the universe. The process begins with simple orbital mechanics. Material falling toward the black hole does not plunge straight in. It has too much sideways motion, so it settles into a flattened, rotating disk like water swirling down a drain. Within this disk, the physics becomes extreme. Layers of gas rub against each other at fantastic speeds, creating immense friction. This friction, along with the twisting of powerful magnetic fields embedded in the plasma, heats the material to unimaginable temperatures. The gas becomes so hot that it does not just glow with visible light. It radiates across the entire electromagnetic spectrum, from intense X-rays to powerful gamma rays, broadcasting the black hole's violent feast across the cosmos. The structure of this disk is a rich source of information. Its inner edge is not arbitrary. It is defined by the innermost stable circular orbit, the final point where material can safely orbit before it is doomed to fall inward. The location of this edge is not fixed. It is dictated by the black hole's spin. A rapidly spinning black hole drags the very fabric of space around with it, pulling this inner edge much closer. By measuring the properties of the light from the inner disk, astronomers can effectively weigh the black hole and measure how fast it is spinning. Sometimes these disks can become unstable. Dense clumps of matter might form, creating sudden, bright flares as they are torn apart and consumed. We have seen this happen at the heart of our own galaxy, with Sagittarius, a star, flashing brightly when it swallows a particularly large lump of gas or even a small star. This incredible power source is the engine behind the most luminous objects in the cosmos, quasars. A quasar is simply a supermassive black hole with a voracious appetite, surrounded by an accretion disk so prodigiously bright that it can outshine its entire host galaxy. The light from these cosmic beacons travels for billions of years to reach us, offering a direct view into the universe's violent youth, when black holes fed aggressively and shaped the galaxies growing around them. Beyond the brilliant maelstrom of the accretion disk lies an even more violent phenomenon. From the very poles of a spinning supermassive black hole, it can launch twin beams of matter, narrow and precise, that scream across space at nearly the speed of light. These are relativistic jets, and they are among the most powerful and efficient engines in the entire cosmos. They are not made of random debris. They are composed of a focused stream of superheated plasma, particles accelerated to energies that dwarf anything we can create in our most powerful particle colliders on Earth. The force required to launch these jets is almost beyond comprehension, channeling the raw power of the black hole's spin and its magnetic fields into a cosmic blowtorch. The leading theory for their formation is a masterpiece of physics. As the black hole spins, it drags the fabric of space-time around with it, an effect known as frame dragging. This motion twists the incredibly powerful magnetic fields that are embedded in the accretion disk, coiling them into a tightly wound, rotating structure. Think of it as a cosmic dynamo. Just as a spinning turbine can generate electricity, the black hole's rotation, coupled with the twisted magnetic fields, acts as a natural particle accelerator. These fields create a narrow channel, a magnetic funnel, that directs some of the infalling material away from the event horizon and blasts it outward from the poles. The jets can stretch for hundreds of thousands of light years, far beyond the boundaries of their host galaxy. We see their spectacular effects in objects like the galaxy Cygnus A, where colossal lobes of radio emission powered by the jets glow on either side of the central galaxy. These jets are not just a spectacular light show, they carry enough energy to sculpt the evolution of entire galaxy clusters. When a jet plows into the thin gas that exists between galaxies in a cluster, it heats that material to millions of degrees, preventing it from cooling down and collapsing to form new stars. This is a critical form of black hole feedback, a self-regulating mechanism where the black hole's own outbursts put a limit on its food supply and the growth of its host galaxy. Without these jets, giant galaxies might continue to form stars until they grew to unimaginable sizes, and the universe would look profoundly different. The radiation from these jets spans the entire spectrum, from intense radio waves to the most energetic gamma rays, making them visible across cosmic distances. By studying them, we learn how a black hole, from its tiny central region, can project its influence across millions of light years, acting as a master architect for the large-scale structure of the universe. These powerful jets and brilliant accretion disks all broadcast a black hole's presence, but they also conceal a deeper mystery. What happens to the identity of the things it consumes? This question lies at the heart of one of the most profound puzzles in modern physics, the black hole information paradox. The problem begins with a fundamental rule of the quantum world. Quantum mechanics states that information about any physical system can never be truly destroyed. If you were to burn a book, its information is not lost. In principle, a being with godlike knowledge could collect all the smoke and ashes, analyze the precise state of every atom, and perfectly reconstruct the original book. Every particle carries a unique identity, a history that must be preserved. Black holes, however, seem to break this sacred rule. When something falls past the event horizon, it is gone forever from our universe. According to Einstein's general relativity, all information about that object, whether it is a book, a star, or an astronaut, is locked away behind the curtain of the event horizon, permanently erased from our reality. This created a stalemate for decades, a quiet acceptance that information was simply lost inside a black hole. Then, in the 1970s, Stephen Hawking made a startling discovery. He realized that black holes are not completely black. Due to strange quantum effects occurring just outside the event horizon, they can slowly leak radiation. This is Hawking radiation. Empty space is not truly empty. It is a seething foam of virtual particles, pairs of particles and antiparticles that constantly pop into existence and then almost immediately annihilate each other. Hawking theorized that when this happens right at the edge of a black hole, one of the virtual particles might fall in while the other escapes. The escaped particle becomes real, carrying away a tiny bit of the black hole's energy. To an outside observer, it looks as if the black hole is emitting a faint glow. Over unimaginable eons, this slow leakage causes the black hole to lose mass and eventually evaporate completely. And here is the paradox: the Hawking radiation that escapes is completely random, like thermal noise. It carries no information about what fell into the black hole. So, if the black hole evaporates and disappears, what happened to all the information about all the things it ever consumed? Was it truly destroyed, violating a cornerstone of physics? This is the information paradox in its starkest form. Solving it has forced physicists to propose radical ideas. One leading solution is the holographic principle. This mind-bending concept suggests that all the information about everything that falls into a three-dimensional black hole is not lost inside. Instead, it is encoded like a hologram on the two-dimensional surface of its event horizon. Think of it like a cosmic DVD. A DVD disc is a flat, two-dimensional surface, but it contains all the information needed to reconstruct a full three-dimensional movie. In the same way, the event horizon might store a perfect, scrambled record of every atom that crossed it. When the black hole evaporates via Hawking radiation, this information is not destroyed. It is slowly and chaotically released back into the universe, imprinted onto the radiation itself. For decades, this was pure theory, but recent advances are bringing it into the realm of testable science. The Event Horizon Telescope, which gave us our first image of a black hole's shadow, may one day be sensitive enough to detect subtle signatures in the light around a black hole that hint at this holographic storage of information. Resolving this paradox is not just an academic exercise, it is the crucial battleground for the ultimate goal of physics, a theory of everything that unifies Einstein's gravity with the quantum world. The fate of information inside a black hole holds the key to understanding the fundamental nature of reality itself. Hawking radiation presents a startling contradiction. A black hole, defined by its absolute darkness, somehow glows. This faint emission arises from the bizarre rules of the quantum world, which govern the smallest scales of reality. Empty space is not a true void. It is a turbulent sea of virtual particles, pairs of matter and antimatter that continuously flicker into existence and then annihilate each other before we can detect them. Normally, this process is perfectly balanced, but at the very edge of an event horizon, this balance is shattered. When a particle pair appears, one particle might fall into the black hole while its partner escapes into space. The escaped particle becomes real, carrying away a tiny amount of energy. To preserve the total energy of the system, the black hole itself must lose a corresponding amount of mass. This is Hawking radiation, a slow and steady leak that causes the black hole to evaporate over time. For a supermassive black hole, this process is almost imperceptibly slow. The rate of evaporation is inversely related to the black hole's mass. A giant with the mass of millions of suns has such a weak Hawking radiation output that it would take trillions upon trillions of years for it to lose any significant mass. In the current age of the universe, this radiation is completely dwarfed by the energy they gain from absorbing cosmic background radiation and occasional gas. Their fate is to grow, not shrink, for eons to come. However, for a much smaller stellar mass black hole, the effect is far more dramatic. Its stronger Hawking radiation would cause it to evaporate at a much faster rate, ending its life in a final, violent burst of gamma rays. Detecting this faint whisper of radiation from a celestial giant remains one of the greatest experimental challenges in physics. While we cannot observe it directly from astrophysical black holes, scientists have created analog black holes in laboratories using supercooled fluids or fiber optics. In these setups, sound or light waves mimic the event horizon, and researchers have observed signatures consistent with Hawking radiation. Confirming its existence would be a monumental step, providing our first direct link between the theory of gravity and the quantum realm, and perhaps finally revealing what happens to information at the end of time. The faint glow of Hawking radiation is a whisper compared to the raw, dynamic power unleashed by a black hole in motion. These cosmic giants are not static pits. They can spin, and some whirl at a significant fraction of the speed of light. This rotation is not a simple curiosity. It is a fundamental property that transforms a black hole from a passive vacuum into an active, energetic engine. We measure this incredible spin indirectly by studying the inner edge of its glowing accretion disk, the point where matter can no longer orbit stably and must plunge inward is called the innermost stable circular orbit. A non-spinning black hole has this orbit relatively far from its event horizon, but a rapidly spinning black hole drags the fabric of space-time around with it, an effect so powerful it pulls this final orbital edge much closer. By using X-ray spectroscopy to map the hot iron gas whipping around in this inner disk, astronomers can pinpoint this edge. The closer the disk gets to the event horizon, the faster the black hole is spinning. This frame-dragging effect, predicted by Einstein, twists the very structure of reality around the black hole, creating a vortex in space-time itself. The implications of this spin are monumental. It is the primary power source for the most violent phenomena in the universe, the relativistic jets. The leading mechanism for this is the Blandford-Zeenagic process. Imagine the black hole's intense rotation coupled with its powerful magnetic fields, which are anchored in the accretion disk. The spinning black hole acts like a gigantic flywheel, winding these magnetic field lines into a tightly coiled, rotating structure. This creates a powerful electric voltage that can extract immense rotational energy from the black hole and funnel it into two narrow beams of plasma shooting out from the poles. It is a cosmic turbine, more efficient than any nuclear reaction, capable of launching jets that cross millions of light years. The spin of a black hole also acts as a historical record, a fossil of its past feeding habits. A black hole that grew primarily by steadily pulling in gas from a consistently rotating accretion disk will have its spin amplified, like a spinning ice skater pulling in their arms to go faster. It can reach the maximum possible speed. In contrast, a black hole that grew through chaotic mergers with other black holes would have received random kicks of angular momentum. These collisions often cancel each other out, leaving the final black hole with a slower, more modest spin. By measuring the spin of a supermassive black hole, we can look back in time and decipher its life story. Was it a voracious, orderly eater or a violent product of cosmic collisions? The answer is written in the speed of its silent, spinning darkness. The spin of a black hole writes its history, but its ultimate legacy is written across its entire galaxy. This is the profound secret of co-evolution, a cosmic dance where the supermassive black hole and its galactic home grow and change together in a tightly linked embrace. It seems counterintuitive that an object so small, relative to the vastness of a galaxy, could wield such influence. Yet, these central black holes act as the ultimate regulators, their power preventing galaxies from spiraling out of control. The key to this control is a process known as feedback. Think of a powerful heating system in a vast building. The accretion disk and relativistic jets pour tremendous energy back into the surrounding galaxy, specifically into the diffuse gas that fills the space between stars. This is the raw material for future star formation. When this gas is heated to millions of degrees, it becomes too energetic to collapse under its own gravity and form new stars. The black hole, in its most active phases, essentially blows away its own food supply. This is a cosmic balancing act of breathtaking precision. In massive galaxies, we see this in the dramatic life cycle of quasars. A quasar is a supermassive black hole feasting so voraciously that its brilliant accretion disk outshines every star in the galaxy. This incredible outburst of energy heats the galactic gas, quenching star formation and putting a hard limit on how large the galaxy can grow. The quasar phase is the galaxy's self-imposed diet, a violent period of regulation that ensures the galaxy does not become impossibly large. Without this feedback, giant galaxies would continue to form stars, growing to sizes that would warp the very fabric of the cosmos as we know it. The evidence for this deep connection is etched into the galaxies themselves. Astronomers have discovered a remarkable correlation between the mass of the central black hole and the properties of the galaxy's central bulge, the dense cloud of stars at its core. The more massive the black hole, the larger and more massive the bulge. This relationship is too precise to be a coincidence. It tells us that the growth of the black hole and the growth of the galaxy are fundamentally intertwined, each regulating the other across billions of years. The black hole is not a passive passenger. It is an active architect using its incredible power to sculpt the structure of its home, ensuring a stable and balanced universe where galaxies can exist as we see them today. Between the familiar stellar mass black holes and the galactic supermassive giants lies a mysterious gap. These are the intermediate mass black holes, the missing link in the cosmic family, with masses ranging from a few hundred to a few 100,000 times that of our Sun. Their existence is crucial, for they could be the long-sought seeds from which the supermassive monsters grew. Yet finding them has proven incredibly difficult, making them one of astronomy's most stubborn ghosts. One leading theory for their birth takes us to the hearts of dense globular clusters, vast swarms of hundreds of thousands of stars gravitationally bound together. In these crowded stellar cities, a runaway process can occur. Through a complex gravitational dance, massive stars can sink to the cluster's core, colliding and merging over and over again. This builds up a single, colossal star that quickly burns through its fuel and collapses, leaving behind a black hole far more massive than any single star could produce alone. Another, more exotic possibility is that they are primordial black holes, formed not from dying stars but from the intense density fluctuations in the very first moments after the Big Bang. These ancient relics would have been woven into the fabric of the cosmos from the beginning, providing ready-made seeds for future growth. So why are they so elusive? Unlike their supermassive cousins, they do not typically sit in gas-rich galactic centers, so they lack brilliant, constant accretion disks to illuminate them. Their gravitational influence is also more subtle, harder to distinguish from the collective pull of many stars in a cluster. The hunt, therefore, relies on catching them in the act of feeding. Astronomers scrutinize ultra-luminous X-ray sources, points of intense X-ray emission located far from galactic centers. The sheer brightness of these sources suggests they are powered by an object larger than a stellar mass black hole but smaller than a supermassive one, a candidate intermediate beast pulling gas from a companion star. More recently, gravitational wave observatories have provided tantalizing clues. The ripples in space-time from merging black holes have revealed collisions involving objects squarely in this intermediate mass range, proving they do exist out in the cosmic dark. Confirming their widespread presence would solve a monumental puzzle. It would provide the missing stepping stones, showing how the first small seeds could have grown through mergers and accretion into the supermassive black holes that dazzled the early universe, lighting up the first quasars when the cosmos was still in its infancy. The silent spin of these giants holds a deeper, more rhythmic secret. When two supermassive black holes, each the heart of a former galaxy, spiral toward each other in a final cosmic dance, they do not collide quietly. Their immense masses churn the very fabric of space and time, sending out ripples known as gravitational waves. These are not waves of light or sound, but literal distortions in reality, stretching and squeezing everything in their path as they travel across the universe at the speed of light. Detecting these particular waves, however, requires a level of patience and precision that pushes the boundaries of science. Because supermassive black holes are so incredibly large, the gravitational waves they produce as they orbit each other have very long wavelengths and low frequencies. A single wave might take years or even decades to pass by Earth. You cannot detect such a slow, cosmic undulation with instruments designed to catch the quick chirps from smaller black holes. So, astronomers turn the galaxy itself into a detector using pulsar timing arrays. Imagine a network of cosmic lighthouses. Millisecond pulsars are the remains of massive stars, spinning hundreds of times per second and emitting beams of radio waves with the metronomic consistency of an atomic clock. By monitoring an array of these pulsars across our galaxy for years, scientists listen for a specific signal. A passing gravitational wave from a distant supermassive black hole binary would minutely alter the distance between Earth and each pulsar. This would cause the incredibly regular ticks from these pulsars to arrive a fraction of a second early or late in a correlated pattern across the sky. It is like listening to a perfectly synchronized orchestra of clocks and hearing a faint, discordant rhythm slowly emerge from the noise, a rhythm written by the slow-motion merger of monsters. The challenge is immense, requiring the combined data from observatories around the world for over a decade to even begin to see a hint of this background hum. But the reward is a completely new understanding of the cosmos. This gravitational wave background is the collective choir of every supermassive black hole binary in the universe. By listening to it, we can census these orbiting giants, understanding how common they are and how they behave in the long eons before a collision. It reveals the hidden history of galaxy mergers, showing us how often galaxies have combined throughout cosmic time to build the large structures we see today. Our current detection methods are just the beginning. The future of this field lies with space-based observatories like the Laser Interferometer Space Antenna, or LISA. This ambitious mission will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, connected by lasers. Free from the seismic noise of Earth, LISA will open a clear, low-frequency window into the universe. It will be able to hear the specific songs of individual supermassive black hole binaries as they spiral closer over years, culminating in the final, thunderous splash of their merger. This will not just confirm their existence, it will allow us to map their masses and spins with incredible accuracy, turning a faint background hum into a symphony of distinct cosmic events. The serene darkness of a dormant black hole can be shattered in an instant. When an unlucky star wanders too close, it is subjected to a gravitational assault of unimaginable violence. This cosmic cataclysm is known as a tidal disruption event. The star does not simply vanish. It is first stretched, pulled into a long, thin strand of stellar material by the immense tidal forces. The black hole's gravity, so much stronger on the side of the star closest to it, literally pulls the star apart against its own self-gravity. This is spaghettification on a stellar scale, a complete and utter shredding of an entire sun. About half of the star's remnants are flung out into the darkness on long, looping trajectories, ejected from the system forever. The other half forms a swirling, chaotic disk of debris around the black hole, a temporary and intensely bright accretion disk. This sudden influx of fuel ignites a spectacular flare of radiation, a beacon that can outshine every star in its host galaxy combined for several months. For a brief, brilliant moment, a quiet and invisible black hole announces its presence with the force of a cosmic supernova. Astronomers treasure these events as perfect natural experiments. In a galaxy where the central black hole is dormant and not actively feeding, it offers very little to observe. A tidal disruption event changes everything. It forces the black hole to reveal its characteristics. The light from the resulting flare holds encoded information about the black hole's mass and its spin. By analyzing how quickly the flare brightens and then fades, scientists can weigh the invisible monster. A more massive black hole will tear a star apart farther from its event horizon, producing a flare that evolves more slowly. A less massive one will only destroy stars that come extremely close, creating a faster, more violent outburst. Each event is a unique laboratory for studying the entire process of accretion, from the initial tidal shredding to the final gulp of stellar material. One of the most famous of these events, known as Assassin 14 Lie, provided an unprecedented look at this process. It was the death cry of a star roughly the size of our Sun, torn apart by a black hole with a mass of several million suns. Observations across the electromagnetic spectrum revealed not just the brilliant flare, but also the telltale signature of stellar debris being devoured. It was like watching a crime scene in slow motion, giving us a detailed forensic analysis of a stellar murder. These events also offer a rare glimpse into the population of stars that swarm perilously close to the galactic center, a region otherwise lost in a blinding crowd of starlight. Each tidal disruption event is a fleeting, violent, and invaluable experiment, a chance to watch a supermassive black hole wake up for a single, spectacular meal. The brilliance of a tidal disruption event is a fleeting spectacle compared to the sustained cosmic fire of an active galactic nucleus. This term describes the intensely bright, compact region at the very center of a galaxy where a supermassive black hole is actively feasting. While they are all powered by the same basic engine, our view of them creates a dazzling bestiary of different objects. The most extreme of these are quasars, the most luminous, persistent objects in the universe. A single quasar can outshine a galaxy of 100 billion stars, its light visible from the very edge of the observable cosmos. Then there are Seyfert galaxies, which appear as normal spiral galaxies but host a brilliantly active star-like core. And blazars present perhaps the most violent face of all, shooting directly at us with jets of radiation so intense they can fluctuate in brightness over mere hours. For decades, astronomers were puzzled by this menagerie. Why did some active cores appear shrouded in dust while others blazed openly? The answer lies not in different types of monsters, but in our perspective. This led to the unified model of active galactic nuclei. Imagine a single, complex machine at the galaxy's center. At its heart is the supermassive black hole and its accretion disk. Surrounding this is a thick, donut-shaped ring of gas and dust called the torus, and shooting out from the poles are the powerful relativistic jets. What we see from Earth depends entirely on our viewing angle. If we look face-on with a clear view of the brilliant accretion disk, we see a quasar. If our view is from the side, the dusty torus blocks our direct line of sight to the brightest inner regions, and we classify it as a different, obscured type of active galaxy. But if one of those high-powered jets is pointed almost directly at us, we see a blazar, its light amplified and its variability extreme due to the relativistic effects of the jet material moving toward us at nearly the speed of light. They are all the same fundamental object, just seen from different cosmic angles. This orientation effect makes these objects perfect probes for studying the distant universe. Quasars act as cosmic lighthouses, their immense brightness allowing us to study the intervening space between them and us. As their light travels for billions of years, it passes through clouds of gas and the faint webs of dark matter that structure the cosmos. These clouds imprint unique absorption lines on the quasar's spectrum, creating a barcode that reveals the composition and distribution of matter across vast cosmic distances. Furthermore, the flickering of an active nucleus is not random noise. By monitoring how its brightness changes over time, astronomers can map the structure of the accretion disk itself. A flicker in the ultraviolet might be echoed moments later by a change in the X-ray emission. This reverberation mapping allows scientists to measure the size of the disk and, by knowing how fast material orbits, calculate the black hole's mass with remarkable precision. Each type of active nucleus, from the steady blaze of a quasar to the frantic flash of a blazar, gives us a unique key to understanding the engine at the center, revealing the mass, spin, and feeding habits of the supermassive black hole that powers it all. The brilliant quasars and violent tidal disruptions represent only a fraction of the story. For every active supermassive black hole blazing across the cosmos, there are thousands of others lying silent and dark. This hidden population of dormant giants makes up the overwhelming majority, sleeping monsters that offer little to no light for our telescopes to find. They are the rule, not the exception. Our own galactic center, Sagittarius, a star, is a perfect example of this quiet state. Despite its immense mass of 4 million suns, it is a faint whisper in the electromagnetic spectrum, emitting only a tiny trickle of energy compared to its active cousins. So how do we confirm the presence of something that gives off almost no light? Astronomers become detectives of motion, meticulously tracking the orbits of stars and clouds of gas swirling around the galactic center. The frantic, high-speed dance of these stars whipping around an apparently empty point in space is the most direct evidence of the black hole's gravitational grip. It is the same method used to weigh Sagittarius, a star, observing the precise paths of stars like S2, which orbits the invisible center at speeds exceeding 10 million miles per hour. This stellar choreography is the undeniable signature of a hidden titan. Periods of dormancy are actually the natural state for most supermassive black holes. They exist in a cosmic feast or famine cycle. A galaxy's central region can simply run out of readily available gas to feed the beast. Without a steady stream of material falling in, the brilliant accretion disk fades away and the black hole falls silent. It is not dead, merely waiting. This quiet can be shattered by a random event. A dense molecular cloud might drift too close, providing a sudden, hefty meal. Or, as we have seen, a star could be torn apart in a tidal disruption event, creating a temporary, brilliant flare that awakens the black hole for a few months before it returns to its slumber. These occasional snacks are what keep our understanding of these dormant giants alive, offering fleeting windows into their properties and reminding us that the silence at the heart of most galaxies is a deep, watchful sleep, not an eternal rest. That deep, watchful sleep may be a temporary state. Our own galaxy holds monumental evidence of a violent past, a time when Sagittarius, a star, was not a quiet giant but an active, eruptive beast. Stretching for 25,000 light-years above and below the galactic plane are two colossal spheres of ultra-hot gas known as the Fermi bubbles. These are not mere clouds, they are vast structures, each one a cosmic ghost haunting the Milky Way, glowing faintly in the most energetic form of light, gamma rays. Their sheer scale is difficult to grasp. If you could see them in the night sky, they would cover half the visible universe, a pair of immense orbs centered on the galactic core. The leading theory for their origin points directly to our central black hole. Astronomers believe that several million years ago, Sagittarius, a star, experienced a tremendous outburst. It was not a full-blown quasar, but a powerful quasar-like event. For a cosmic instant, the black hole feasted on a large amount of gas, and its accretion disk flared with intense brilliance. This activity did more than just produce light. It launched a pair of powerful jets or a massive wind of energetic particles straight out from the galactic center, punching through the thin gas of the galactic halo. These jets inflated the Fermi bubbles, filling them with superheated plasma and accelerating particles to near light speed, causing them to radiate the gamma rays we detect today. The bubbles are a fossil record, a preserved snapshot of that ancient cataclysm. By studying their size and the energy required to create them, scientists can work backwards. They can estimate the power of that long-ago eruption and its duration, which might have lasted for tens of thousands of years, a brief but transformative scream in the life of our galaxy. This means the Milky Way was once a very different place, its center blazing with an intensity that would have been visible from distant galaxies. Our black hole is not eternally dormant. It has a cycle of sleep and activity, and the Fermi bubbles are the permanent scars from its last great awakening. We are not unique in this. Astronomers have observed similar giant bubbles and X-ray cavities around other galaxies like the Perseus cluster. These structures are the universal signature of past black hole outbursts, proving that this cycle of violent feedback is a fundamental process that has shaped not just our home, but galaxies across the cosmos. Far from the galactic center, a different kind of beacon pulses in the X-ray sky. These are the ultraluminous X-ray sources, or ULQs, and they present a profound puzzle. They shine with the power of millions of suns, but they are not anchored in the hearts of galaxies. They are found in the spiral arms, in star-forming regions, and in dwarf galaxies, isolated and brilliant. For a long time, their sheer luminosity defied explanation. A typical stellar mass black hole, formed from a single dying star, simply cannot accrete matter fast enough to shine so brightly. There is a theoretical limit called the Eddington limit, which is the maximum brightness an object can achieve when the outward pressure of its own radiation balances the inward pull of its gravity. Exceed this limit, and you would theoretically blow away the very accretion disk that feeds you. Yet ULXs blaze right through this limit, some shining hundreds of times brighter than they should be able to. This forced astronomers to consider two radical possibilities. The first is that we are seeing intermediate mass black holes in the wild, those elusive missing links with masses of a few hundred to a few thousand suns. A black hole of that size would have a much higher Eddington limit, allowing it to shine brightly without violating the laws of physics. The second, more exotic idea is that these are not intermediate mass monsters at all, but rather ordinary stellar mass black holes that are feeding in an extraordinary way. They might be accreting material at a supercritical rate, piling on so much gas so quickly that the radiation is trapped and funneled, creating a thick, puffed-up disk that acts like a cosmic nozzle, directing intense beams of X-rays out into space. If one of those beams happens to be pointed at Earth, the source would appear far brighter than it truly is, like a lighthouse beam sweeping across a dark ocean. So how do we tell which scenario is correct? The key lies in the subtle details of their X-ray light. By analyzing the spectra, the unique fingerprint of energy emitted by these objects, astronomers can probe their environment. Some ULXs show signatures of incredibly strong magnetic fields, trillions of times more powerful than anything on Earth. This points to a specific type of stellar remnant called a magnetar, a neutron star with a ferocious magnetic field, which could potentially power these brilliant sources without needing a black hole at all. Others, however, show variability in their X-ray output, flickering in a specific way that suggests the presence of a small, dense object, a stellar mass black hole accreting matter at a furious, unstable rate. The hunt is ongoing, with each new ULX discovery offering a fresh clue. They represent a diverse population, not a single type of object. Some are indeed confirmed to be neutron stars, proving that stellar corpses can, under the right conditions, break the Eddington limit and masquerade as larger beasts. Others remain strong candidates for the true intermediate mass black holes, feeding quietly in the cosmic countryside. Their very existence challenges our neat categories and reveals that black holes can grow and shine in unexpected places, far from the grand galactic stages they usually command. Magnetic fields are the invisible architects shaping the chaos around a black hole. While gravity pulls everything inward, it is these intense magnetic fields that direct the flow, channeling the fury into structured and powerful outflows. The process begins deep within the churning plasma of the accretion disk. As the superheated gas spirals inward at fantastic speeds, its charged particles create electrical currents. These currents, in turn, generate magnetic fields. This self-reinforcing loop acts like a cosmic dynamo, amplifying weak seed fields into colossal structures that weave through the entire disk. These fields do not just sit there, they perform a critical job solving a fundamental puzzle of accretion. For matter to fall into the black hole, it must lose its immense angular momentum, its sideways motion. The magnetic fields act as a cosmic brake, creating friction between different layers of the spinning disk. This magnetic friction robs the material of its orbital energy, allowing it to spiral inward and finally cross the event horizon. Without this process, matter would simply orbit forever, never feeding the monster at the center. But their most spectacular role is in launching the relativistic jets. The black hole's spin drags these magnetic field lines, twisting them into a tightly wound, rotating coil. This structure acts like a giant slingshot, flinging charged particles outward along the black hole's rotation axis. The magnetic fields funnel and collimate this eruption, squeezing it into two narrow, focused beams that can punch through an entire galaxy. This is the essence of the Blandford-Zeenagic process, a mechanism that directly taps the rotational energy of the black hole itself, converting the spin of spacetime into a raw galactic-scale power source. We are not just theorizing about these forces, we can now see them. The iconic image of the black hole in galaxy M87, captured by the Event Horizon Telescope, revealed more than just a shadow. The specific pattern of polarized light in the fiery ring is a direct map of the magnetic field lines at the very edge of the event horizon. This polarization is created by synchrotron radiation, the light emitted when electrons spiral at near light speed along powerful magnetic fields. By reading this cosmic compass, astronomers confirmed that the magnetic fields are strong and highly organized, exactly as the models predicted for launching those tremendous jets. These fields are the enduring engine. While a black hole's food supply may be intermittent, its stored spin energy is vast. A strong magnetic field can act as a permanent tap, allowing the black hole to power its jets for billions of years, long after its last major meal, shaping the destiny of its galactic home from the silent, spinning dark. That first image of a black hole shadow was not a photograph in any ordinary sense. It was a monumental achievement of computational reconstruction, a picture painstakingly assembled from petabytes of data collected by a telescope the size of our planet. The dark central void we see is not the event horizon itself. That boundary is fundamentally unseeable. Instead, this shadow is the silhouette of the event horizon cast against the brilliant, glowing backdrop of its own accretion disk. It is the black hole's gravitational pull creating a dark deficit in the light that surrounds it, a perfect circle of nothingness that reveals everything. The size and shape of this shadow are not random. They are determined by the black hole's two fundamental properties, its mass and its spin. A more massive black hole casts a larger shadow. A rapidly spinning black hole, which drags spacetime into a vortex around it, will distort the shadow, making it appear slightly flattened on one side, like a crescent rather than a perfect circle. Comparing the iconic images of M87's black hole and our own Sagittarius, a star, reveals these subtle differences, telling the unique story of each cosmic giant. To capture such a tiny shadow from millions of light years away required an instrument of almost impossible sharpness, a telescope with a resolution fine enough to read a newspaper on the surface of the Moon from Earth. This is where the Event Horizon Telescope achieved the impossible. It is not a single dish but a global network of radio observatories from the high deserts of Chile to the frozen peaks of Hawaii and the South Pole. Using a technique called very long baseline interferometry, these widely separated telescopes synchronized their observations with atomic clocks, all pointing at the same black hole at the same time. The distance between them, the baseline, effectively creates a virtual telescope as wide as the entire Earth. Each pair of telescopes captures a specific frequency, a single note in the cosmic symphony of the black holes surrounding light. With enough of these notes collected from across the globe, scientists can use complex algorithms to reconstruct the source image, much like piecing together a musical chord from its individual frequencies. The challenges were staggering. The weather had to be perfectly clear at every single observatory site simultaneously. The data volumes were so immense they could not be sent over the internet. They had to be physically shipped on hard drives to central processing centers. Then began the meticulous work of correlating the signals and assembling the final picture, a process that took years of supercomputer time and human ingenuity. The future promises an even sharper view. The next leap will come from placing radio telescopes in space, extending the virtual baseline far beyond the diameter of Earth. A space-based array could capture details an order of magnitude finer, allowing us to see the intricate dynamics of plasma flowing around the event horizon, and perhaps even spot the flash of a star being torn apart in a tidal disruption event. We are on the verge of moving from still images to movies of black holes, watching these cosmic monsters breathe and feed in real time. The fictional gargantua from the film Interstellar offers more than just stunning visuals. It serves as a gateway to the truly exotic physics that govern a rapidly spinning supermassive black hole. While the movie took artistic license, its portrayal of a colossal, spinning black hole was grounded in real science, pushing our understanding of reality to its absolute limit. One of the most bizarre regions surrounding such a black hole is the ergosphere. This is an oval-shaped zone of distorted space that lies outside the event horizon. Within the ergosphere, the frame-dragging effect is so powerful that space itself is dragged around the black hole faster than the speed of light. Nothing here can stand still. Every particle, every speck of dust is forced to rotate with the black hole, caught in a cosmic current from which there is no escape. This strange property leads to a remarkable theoretical possibility, the Penrose process. Imagine an object entering the ergosphere and splitting in two. One piece falls into the event horizon while the other escapes. Under very specific conditions, the escaping fragment could carry away more energy than the original object possessed. It essentially steals a portion of the black hole's rotational energy, causing the black hole to spin slightly slower. This is not a perpetual motion machine, but a real, if highly theoretical, consequence of Einstein's equations. It shows that a black hole's spin is not just a property, but a tangible reservoir of power that could, in principle, be mined. Such extreme environments also force physicists to consider even wilder possibilities embedded in their equations, like wormholes. These hypothetical tunnels through spacetime, also known as Einstein-Rosen bridges, are valid mathematical solutions to the equations of general relativity. They could, in theory, create a shortcut between two distant points in the universe, or even connect two different universes entirely. However, the science is very clear on one point. Any naturally occurring wormhole would be incredibly unstable. It would collapse into a singularity in an instant unless it was propped open by a form of matter with negative energy density, something we have never observed. While interstellar travel through a wormhole remains firmly in the realm of science fiction, its theoretical existence highlights the profound strangeness of the cosmos. Black holes are not just endpoints for matter. They are cosmic laboratories where the known laws of physics are stretched and broken, compelling us to search for a deeper theory that can describe reality at its most extreme. The faint glow of Hawking radiation holds a startling implication. Even the mightiest supermassive black hole is not entirely permanent. Given enough time, they can evaporate completely. This process is governed by a strange and counterintuitive relationship. The temperature of a black hole is inversely proportional to its mass. A smaller, stellar mass black hole is incredibly hot and emits Hawking radiation at a significant rate, leading to a relatively swift demise. But a supermassive black hole with the weight of millions of suns is profoundly cold. Its Hawking radiation is just a faint whisper, a trickle of particles so slow that it is utterly overwhelmed by the cosmic microwave background, the leftover heat from the Big Bang that still fills the universe. For a giant like Sagittarius, a star, the energy it loses through this quantum leak is less than the energy it gains from simply bathing in the warm glow of space. Its growth for now continues. The timeline for this evaporation is almost beyond human comprehension. A typical supermassive black hole would take trillions upon trillions of years to lose even a fraction of its mass. This is a timescale so vast that all stars will have long since burned out, galaxies will have drifted apart, and the universe will be a dark, cold, and empty expanse. In that distant, frozen era, black holes may be the last significant structures in existence, the sole landmarks in an endless night, and then, one by one, they too will begin to fade. As a black hole evaporates, it loses mass. As it loses mass, its temperature rises, which in turn increases the rate of evaporation. The final moments are not a slow fade, but a sudden, violent detonation. In a flash of high-energy particles, the black hole would vanish, returning all its accumulated mass back to the universe as a burst of radiation. What happens to all the information about everything it ever consumed? According to some interpretations, that information is finally released, imprinted onto the last burst of Hawking radiation, resolving the paradox in a final, cosmic exhale. This ultimate fate forces us to confront the deepest cycles of the cosmos, where even the most permanent-seeming giants are merely temporary features in an ever-changing universe. The silent, invisible presence of dark matter might hold a secret connection to the monsters at the Galactic Center. While we cannot see dark matter directly, we know it exists by its gravitational pull, forming a vast, diffuse halo that envelops every galaxy. Some theories suggest this mysterious substance interacts with supermassive black holes in profound ways. Imagine dark matter particles swarming around the black hole, drawn in by its immense gravity. They would not fall in to be consumed like normal matter, as they rarely interact with each other or with light. Instead, they could accumulate in an incredibly dense spike, a thick cloud of shadowy particles right at the black hole's doorstep. This dense concentration could subtly alter the black hole's growth and even produce a faint, telltale signal. As these dark matter particles collide within the spike, they might annihilate each other, releasing a burst of gamma rays, the most energetic form of light. Astronomers are actively scanning the regions around supermassive black holes, searching for this unique, high-energy fingerprint that could finally reveal dark matter's identity. Another more radical idea proposes that dark matter itself could be made, at least in part, from black holes. These would not be the giants we see today, but tiny, primordial black holes forged in the intense heat of the Big Bang's first moments. If these ancient relics exist in vast numbers, they could be the unseen mass that binds galaxies together. In this scenario, the first supermassive black holes may have grown from these primordial seeds, providing the massive head start needed to explain the quasars in the early universe. The hunt for evidence is underway. Scientists use gravitational lensing, watching how the gravity of a black hole and its potential dark matter spike bends light from background stars, looking for the distinctive warping that only concentrated mass can create. Each observation brings us closer to understanding if the two greatest mysteries of the cosmos, dark matter and supermassive black holes, are inextricably linked in a hidden cosmic dance. At the very heart of this cosmic giant, beyond the event horizon and past the point of spaghettification, lies the final frontier of physics itself. This is the singularity, the true core of the black hole where all the mass is crushed into a point of infinite density. The equations of general relativity, which so beautifully describe the warping of space and time around the black hole, break down completely here. They predict a place where gravity becomes infinite and the fabric of reality ceases to exist as we know it. But nature abhors infinity. This mathematical warning sign tells us we are missing a crucial piece of the puzzle, a theory that can marry the vast scales of gravity with the tiny, probabilistic world of quantum mechanics. We need a theory of quantum gravity. The quest for this ultimate theory has led physicists down two fascinating and very different paths. String theory proposes that the fundamental constituents of reality are not point-like particles, but incredibly tiny, vibrating strings. The different vibrations of these strings would produce all the particles and forces we observe, with gravity naturally emerging from the symphony. In this view, the singularity might be replaced by a tiny, dense knot of these strings, a structure with a finite size that avoids the paradox of infinite density. The other major contender is loop quantum gravity. This approach suggests that space itself is not smooth and continuous, but is woven from a fabric of tiny, finite loops. Think of spacetime as a cosmic tapestry with a smallest possible stitch. At the black hole's center, this fabric would not tear into an infinite point. Instead, the extreme gravity would cause these loops to rebound, transforming the singularity into a hypothetical object called a Planck star. This would be a ball of spacetime under immense quantum pressure, a moment of ultimate density that then rapidly expands into a new region of the universe. This idea is profoundly radical, suggesting that a black hole could be a gateway to another cosmos, a big bang on the other side of the veil. Understanding what truly happens at the singularity is not just an academic exercise. It is the key to resolving the information paradox we encountered earlier. If the singularity is a true endpoint, information is lost forever. But if quantum gravity replaces it with a finite structure, like a Planck star or a fuzzball from string theory, then information has a place to be stored and potentially released. The fiery debate over the singularity forces us to confront the very nature of reality. Is spacetime ultimately smooth, or is it granular? Can we truly have a beginning to the universe, or are black holes birthing new ones in the darkness? The answers hidden within the heart of these monsters hold the potential to finally unify physics and reveal the ultimate laws of the cosmos. This warping of space does far more than just trap light. It twists the very path that light travels, creating one of general relativity's most spectacular predictions. Gravitational lensing turns a black hole into a cosmic magnifying glass, one that distorts and multiplies the images of anything behind it. Picture a single, distant galaxy situated perfectly behind a supermassive black hole from our viewpoint. The black hole's immense gravity acts like a flawed lens, bending the galaxy's light around itself. Instead of seeing one galaxy, we would see multiple smeared copies of it, stretched into luminous arcs encircling the central darkness. In a perfect alignment, this creates an Einstein ring, a complete circle of light surrounding the black hole's shadow, a halo forged by distorted spacetime. These are not mere illusions, they are precise cosmic tools. By measuring the distortion of these background objects, astronomers can map the black hole's gravitational field with incredible accuracy, weighing it independently of the stars orbiting it. This provides a crucial test of Einstein's theory in the most extreme environment imaginable. But the distortion is not limited to light. Time itself becomes a casualty of this intense gravity. According to general relativity, time passes at different rates depending on the strength of the gravitational field. Near the event horizon of a supermassive black hole, where gravity is almost immeasurably strong, time slows down dramatically compared to the rest of the universe. Imagine a hypothetical spacecraft on a mission to orbit just outside the event horizon. The crew might experience the passage of a single hour, completing their observations and data collection. But for everyone else in the universe, for mission control back on Earth, thousands of years would have passed. They would return to a civilization utterly transformed, their loved ones long gone, their world unrecognizable. This time dilation is not science fiction. It is a measurable effect. The GPS satellites orbiting our own planet have to account for tiny time shifts caused by Earth's much weaker gravity, or their navigation would fail within minutes. Near a black hole, this effect is magnified to an unimaginable extreme. This creates a profound and isolating paradox. An observer watching the doomed spacecraft from a safe distance would see its clock ticking slower and slower, its image reddening and dimming as the light struggles to escape the gravitational well. The ship would appear to freeze in time, hovering eternally at the edge of the void, never quite crossing from the outside perspective. These bizarre distortions of light and time are not just theoretical curiosities. They are the definitive signatures of warped space-time, allowing us to probe the very nature of reality and confirm that the universe operates by rules far stranger than our everyday experience suggests. The silent dance of two titans begins with a galactic collision. When two galaxies merge, their central supermassive black holes are drawn together in a cosmic courtship that can last for billions of years. This is the mystery of black hole binaries, a pair of invisible giants locked in a gravitational embrace at the very heart of a newly formed galaxy. Their journey toward each other starts with a process called dynamical friction. As the black holes move through the dense stellar environment of the galactic core, their immense gravity pulls stars toward them. These stars swing around the black holes, stealing a tiny bit of their orbital energy and momentum. It is like wading through a thick crowd where every interaction slows you down. This friction causes the black holes to spiral inward, drawing closer over eons until they are close enough to form a stable binary system, orbiting a common center of gravity. For a long time, they continue this slow waltz, separated by a distance of a few light years. At this stage, their primary signature is not gravitational waves, but light. Astronomers hunt for them by looking for periodic variations in the brightness of quasars. If one black hole in the binary has an active accretion disk, its orbit will cause the light we receive to brighten and dim in a regular, repeating pattern as it moves toward and away from us. Another telltale sign appears in the spectrum of the active galaxy. The swirling gas in the accretion disks can produce double-peaked emission lines. Instead of a single, sharp peak in the light's fingerprint, we see two distinct peaks, one redshifted and one blueshifted, created by the two separate disks of the orbiting pair. These are the ghosts in the spectral data, the hints of a double heart beating within a single galaxy. The final act of this cosmic ballet is the most violent and revealing. As the binary orbit tightens, the black holes begin to lose energy by radiating gravitational waves, those ripples in spacetime predicted by Einstein. This emission causes their orbit to decay inexorably, spinning them faster and faster until they finally coalesce in a cataclysmic merger. This event releases more energy than all the stars in the observable universe combined for a brief, spectacular instant, a flash of pure gravitational power. Detecting these binaries at every stage is crucial. They are direct evidence of the galaxy merger process, allowing us to measure how often galaxies have combined throughout cosmic history. Their final merger is the ultimate laboratory for testing general relativity in the strong field regime, where gravity is at its most extreme and our theories are pushed to their absolute limit. Finding them confirms that the universe's largest structures are built through a slow, violent, and rhythmic process of collision and consolidation. The immense power of a single black hole reverberates far beyond its host galaxy, shaping the very architecture of the cosmos. These titans act as master regulators for the largest structures we know, galaxy clusters, which are vast metropolises of hundreds or even thousands of galaxies bound together by gravity. The space between these galaxies is not a perfect vacuum. It is filled with a thin, superheated gas known as the intergalactic medium. This gas should, in theory, cool down over time, collapse under its own weight, and form trillions of new stars. But that is not what we observe. The gas remains hot and diffuse, and star formation in these clusters is mysteriously quenched. The culprit is the collective outburst from the supermassive black holes at the center of many cluster galaxies. Their relativistic jets, those narrow beams of energy we discussed earlier, plow directly into this intergalactic gas. They act like cosmic blowtorches, injecting immense heat and stirring the gas into a turbulent, simmering state, preventing it from ever cooling enough to create new stars. We can see the evidence for this in stunning X-ray images of clusters like Perseus, where vast, dark cavities, bubbles carved out by the jets, punctuate the glowing hot gas. This is black hole feedback on a truly colossal scale, a self-regulating mechanism that prevents galaxy clusters from becoming impossibly large and dense, maintaining a cosmic balance that defines the modern universe. This influence stretches back to the very dawn of time. In the early universe, before the first galaxies fully formed, the cosmos was filled with a neutral fog of hydrogen gas. Something had to clear this fog, to rip electrons away from their nuclei in a process called reionization. The intense ultraviolet light from the first quasars, which are supermassive black holes in their most voracious feeding phase, is a prime suspect. These brilliant beacons acted as cosmic lighthouses, their radiation flooding the universe and burning away the primordial haze, rendering the universe transparent to light and allowing the first galaxies to be seen. This was a pivotal moment, and the growth of these early black holes is deeply intertwined with the formation of the cosmic web, the vast filamentary network of dark matter that forms the skeleton of the universe. Supercomputer simulations reveal this intricate dance. They show how the first black holes formed at the dense nodes where these dark matter filaments intersected. Their powerful outflows then regulated the flow of gas along these cosmic highways, funneling it toward the growing galaxies or heating it to suppress star formation in the voids. In these virtual universes, the relatively tiny black holes, mere specks compared to the vast filaments, act as control valves. Their explosive feedback governs how much gas is available to build galaxies, determining their final sizes, shapes, and populations. Without these energetic eruptions, the universe would look profoundly different. Galaxies would be far more massive, stars would form in uncontrolled bursts, and the delicate cosmic web we observe today might be a tangled, overgrown jungle. The supermassive black hole is not just a resident of its galaxy. It is a fundamental architect, its voice a whisper of gravity that echoes across millions of light years to sculpt the largest structures in existence. These ancient relics could be the universe's original black holes. Primordial black holes are a theoretical concept, born not from dying stars but from the raw chaos of the cosmos's first moments. In the intensely hot, dense soup that existed just after the Big Bang, random fluctuations in density could have been so extreme that pockets of space collapsed under their own weight, pinching off into tiny, potent black holes. This means they could have formed before the first stars even ignited, making them potential seeds for the supermassive giants we find at galactic centers today. Imagine a universe filled with countless tiny specks of infinite density, each a potential starting point for a future cosmic monster. These primordial seeds, with masses ranging from that of a small asteroid to thousands of suns, would have had a colossal head start, providing the building blocks that could grow through billions of years of accretion and mergers into the behemoths that power quasars in the early universe. The hunt for them, however, has proven incredibly difficult. How do you find something that could be the size of a mountain but contain the mass of a planet and that emits almost no light? Astronomers use clever indirect methods. One is gravitational microlensing. If a primordial black hole passes directly between us and a distant star, its gravity will act as a lens, briefly magnifying the star's light. By monitoring millions of stars for these characteristic brightenings, surveys have placed strict limits on how many such objects could be lurking in the halo of our galaxy. So far, these searches have not found the vast populations that would be needed if they were the primary constituent of dark matter. Similarly, observations of gravitational waves from merging black holes provide another constraint. The masses and frequencies of the black hole mergers we have detected so far do not match the predictions for a universe densely populated with a specific range of primordial black holes. The data tells us they cannot make up all of dark matter, but they could still be a fascinating component. The tantalizing possibility remains that a fraction of the universe's mysterious missing mass is in the form of these ancient fossils. Future observatories will take up the hunt with even greater sensitivity. The Nancy Grace Roman Space Telescope will perform microlensing surveys of unprecedented scale, scanning the crowded central bulge of our galaxy for the telltale flashes caused by these invisible drifters. If they are out there, we are on the verge of discovering a hidden population that has existed since the very beginning, a living record of the universe's most violent birth pangs, and perhaps the long-sought seeds of the giants that rule the cosmos today. Even the darkest abyss in the universe might have a temperature. This is the bizarre world of black hole thermodynamics, a set of laws that treats a black hole not as a simple pit, but as a complex thermodynamic system with its own entropy and heat. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking made a startling leap. They proposed that a black hole's properties, its mass, its electric charge, and its spin, could be perfectly mapped onto the classic laws of thermodynamics. The black hole's mass is analogous to its energy. Its surface gravity corresponds to temperature, and most profoundly, the area of its event horizon is directly linked to its entropy. Entropy is a measure of disorder, of the number of ways you can rearrange the microscopic components of a system without changing its overall appearance. For a black hole, this entropy is unimaginably vast. It is proportional to the surface area of its event horizon. Every time a black hole swallows a bit of matter, the area of its event horizon increases, and so does its entropy. This is a cosmic ledger permanently recording everything that has fallen in. The implications of this are staggering. In ordinary systems, entropy is related to volume. A box of gas has more possible states, more entropy, the bigger its volume. But for a black hole, entropy is tied to its surface area. This peculiar fact led to the holographic principle, a concept so radical it reshapes our understanding of reality. The principle suggests that all the information about everything that has ever fallen into a three-dimensional black hole is not stored in its volume. Instead, it is encoded like a hologram on the two-dimensional surface of its event horizon. Think of it as the universe's ultimate data storage device. A credit card's hologram is a two-dimensional surface that projects a three-dimensional image. In the same way, the event horizon might hold a perfect, scrambled record of every atom, every planet, and every star it has consumed, with all that information painted onto its spherical surface. This provides a potential solution to the information paradox. When the black hole evaporates via Hawking radiation, the information is not destroyed. It is slowly and chaotically released back into the universe, imprinted onto the radiation itself. This incredible connection weaves together the three great pillars of modern physics: gravity, quantum mechanics, and information theory, suggesting that the universe at its most fundamental level might be a vast cosmic hologram. The extreme gravity of a supermassive black hole carves its immediate surroundings into a chaotic stellar metropolis. Hundreds of stars swarm in a dense, frenetic cluster, whipping around the central void at speeds exceeding 10 million miles per hour. These are the S-stars, a group of young, massive stars whose orbits are a direct test of Einstein's universe. Their paths are not neat circles but highly elliptical, tracing a rosette pattern as they make their closest approach. This orbital dance, precisely tracked for decades, reveals a subtle forward shift in their closest point to the black hole, a phenomenon called Schwarzschild precession. It is a perfect, natural validation of general relativity, a wobble in the fabric of spacetime itself caused by the black hole's immense mass. Watching these stars is like seeing the universe's most fundamental laws written in fire across the galactic core. This dynamic environment is not just for stars. Could planets exist in such a violent neighborhood? Theoretically, yes, but their origins would be as dramatic as their surroundings. Some might form directly within the tumultuous accretion disk, coalescing from the swirling gas and dust in a process known as circum-black hole planet formation. These would be strange, transient worlds, born in a maelstrom of intense radiation and gravitational stress. Others could be survivors, planets ripped from their parent stars during a close encounter with the black hole and flung into wide, lonely orbits around the abyss itself. The habitability of such a world, however, is a profound challenge. The relentless gravitational tides would constantly stress the planet's crust, triggering global volcanic activity. The radiation from the hot accretion disk and the surrounding star cluster would bathe the surface in a sterilizing glow. A year on such a planet might last only a few Earth hours, a frantic sprint around the darkness. Yet, for any hypothetical observer on its surface, the sky would present a view beyond imagination. The central black hole would not be a void, but a dark sphere encircled by a brilliant, warped ring of light from the accretion disk, with the crowded stellar cluster shining like a permanent, dense galaxy overhead. It would be a front-row seat to the most extreme physics in the cosmos, a terrifying and beautiful perspective on the power that shapes galaxies. The serene rule of a supermassive black hole can be violently disrupted. These cosmic titans can be physically kicked out of their galactic thrones. This astonishing phenomenon, a black hole kick, occurs during the final moments of a merger between two supermassive black holes. As they spiral together and coalesce, they emit gravitational waves, those ripples in spacetime. If the merger is perfectly symmetrical, the waves radiate evenly in all directions. But nature is rarely so orderly. If the two black holes have unequal masses or misaligned spins, the final burst of gravitational waves can be shot out like a cannon in one preferred direction. The newborn black hole recoils in the opposite direction, obeying the same law of physics that causes a gun to kick back against your shoulder. This recoil can be powerful enough to fling the merged black hole clear out of the galactic center at speeds of millions of miles per hour. Imagine the aftermath. A galaxy, having just undergone a colossal merger, finds its central gravitational anchor, its primary source of feedback, suddenly gone. The very heart of the system has been torn out and sent hurtling into the darkness. Astronomers are now actively hunting for these wandering black holes. They search for the brilliant, telltale flare of a quasar shining from the distant halo of a galaxy, or even from the emptiness of intergalactic space, far from any stellar population that could otherwise explain its presence. Finding one would be a direct confirmation of this extreme physics in action. The implications for the host galaxy are profound. The central black hole is the primary regulator of star formation. Its powerful jets and radiation heat gas and suppress the birth of new stars. If that black hole is ejected, this vital feedback mechanism is severed. The galaxy could experience a runaway burst of star formation, consuming its gas reserves in a short, brilliant blaze. Its growth would become unchecked, its structure fundamentally altered. A kicked black hole is a cosmic catastrophe, an event that can rewrite the future of an entire galaxy, proving that even the most powerful objects in the universe are not immune to being thrown out into the cold. The most violent explosions since the Big Bang may have a monstrous architect. Long-duration gamma-ray bursts are cosmic detonations so powerful they can release more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifetime. For decades, their origin was a profound mystery, but a compelling theory now points a finger at the supermassive black holes lurking in galactic centers. The engine for this unimaginable violence is the same mechanism that creates the relativistic jets we have discussed, but pushed to its absolute extreme. Picture a supermassive black hole suddenly gifted with a colossal feast, perhaps from the tidal disruption of an entire star cluster or the chaotic merger of two black holes in a dense stellar environment. This provides a massive, rapid infusion of fuel. The black hole's accretion disk becomes a tempest of superheated plasma, and its magnetic fields coil into an impossibly tight spring. The resulting relativistic jets are not just powerful, they are ultra-relativistic, focused into needle-thin beams of particles moving at 99.9% the speed of light. When these unimaginably fast jets slam into the dense clouds of gas and dust surrounding the galactic nucleus, the collision is apocalyptic. The jets transfer their colossal kinetic energy almost instantly into radiation, creating a fireball of high-energy gamma rays. It is the cosmic equivalent of a sonic boom, but written in the language of pure light. This model elegantly connects two of the universe's most energetic phenomena. Observations are beginning to find the smoking gun. Astronomers have detected long gamma-ray bursts whose locations appear coincident with the nuclei of their host galaxies, the very domain of supermassive black holes. In these cases, the burst is not from a random star in a spiral arm, but from the central heart of darkness itself. This suggests a scenario where a sudden, catastrophic influx of material onto the black hole, a stellar demolition derby at the galactic center, triggers a jet that punches its way out, lighting up the cosmos with a brief, terrifying flash. This potential link deepens the mystery of gamma-ray bursts, transforming them from isolated stellar catastrophes into possible symptoms of the violent life cycles of the universe's most massive objects. It suggests that the supermassive black hole is not just a silent guardian or occasional feeder, but can, under the right conditions, become a bomb of cosmic proportions. The heart of a black hole might be a gateway to another reality. This idea pushes beyond the known laws of physics into the realm of speculative cosmology, where supermassive black holes are not endpoints but potential creators. Some theories suggest that the singularity at a black hole's core, the point of infinite density, does not mark the end of space and time. Instead, it could be a bridge, a cosmic tunnel that leads to a completely different universe. This hypothetical passage is known as a wormhole, or more technically, an Einstein-Rosen bridge. In this view, our universe might be studded with these portals, each one the dark heart of a supermassive black hole leading to another cosmic realm. The concept becomes even more radical with the idea of a bouncing singularity. In loop quantum gravity, the immense pressure at the center does not lead to an infinite point. Instead, the fabric of spacetime rebounds, transforming the black hole's core into something called a Planck star. This rebound could be so violent and expansive that it triggers a new Big Bang, birthing an entire baby universe within its own spacetime bubble. Our entire cosmos in this breathtaking scenario could have been born from the singularity of a black hole in a parent universe. This is not a one-time event. It suggests a cyclical or branching multiverse, an endless tree of universes sprouting from the corpses of their predecessors. The challenge, of course, is that these ideas are currently untestable. Anything that passes through a black hole's event horizon is lost to our universe forever, its data seemingly erased. We cannot send a probe or observe what happens beyond that final boundary. The theories rely on mathematical elegance and consistency rather than direct experimental proof. They find a natural home in frameworks like string theory, which posits extra dimensions of space that could allow for such bridges between cosmic domains. If these speculative ideas hold any truth, the philosophical implications are staggering. Every supermassive black hole could be a universe in its own right, a cosmic matryoshka doll of realities nested within realities. The laws of physics in that newborn universe might be subtly different from our own, determined by the chaotic conditions of its birth. This transforms the black hole from a simple destroyer into a potential creator, a cosmic seed for an infinity of new worlds. It is the ultimate expression of cosmic recycling, where death on one scale gives birth to existence on another. The void itself is a cosmic accelerator, capable of hurling fragments of atoms across the universe with incomprehensible force. These are cosmic rays, not rays of light but subatomic bullets, protons, and atomic nuclei traveling at nearly the speed of light. Their energies can dwarf anything produced in our most powerful particle colliders on Earth by millions of times. For decades, the origin of the very highest energy cosmic rays was one of astronomy's greatest mysteries. How could nature forge such powerful projectiles? The answer appears to lie in the violent storms surrounding supermassive black holes. The primary engine for this particle acceleration is the relativistic jet. Within these narrow beams, chaotic and powerful shock waves ripple through the magnetized plasma. Think of a particle as a pinball caught in a cosmic maze of magnetic fields. It bounces back and forth across a shock front, a turbulent boundary where the jet's flow slams into slower moving material or even into itself. With each crossing, the magnetic fields give the particle a slight kick, a boost of energy. Over countless cycles, this diffusive shock acceleration can propel a single proton to energies that defy belief. It is a natural particle accelerator of staggering efficiency and scale. Another potent source arises from the accretion process itself. Vast shocks can form in the inflowing rivers of gas, especially when galaxies collide and send chaotic streams of matter toward the central black hole. These accretion shocks create another type of natural accelerator, capable of boosting particles to extreme energies. The evidence linking these cosmic bullets to black holes is compelling. Observatories like the Pierre Auger Observatory, which spans miles of desert, have traced the paths of the most energetic cosmic rays back to broad regions of the sky populated by active galactic nuclei. While we cannot pinpoint a single source with absolute certainty, the statistical correlation is strong. These ultra-high-energy particles are the messengers from the most violent neighborhoods in the universe. By catching them, we are indirectly probing the fierce conditions within those relativistic jets and accretion shocks. Each proton that strikes our atmosphere carries encoded information about the magnetic fields and turbulent physics that launched it on its billion-year journey. They offer a unique window into the black hole's environment, allowing us to study the workings of its powerful engine from the safety of our own galactic backyard. Yet a profound puzzle remains. The very highest energy cosmic rays are so powerful that they should be slowed and degraded by collisions with the faint afterglow of the Big Bang, the cosmic microwave background over long distances. Their detection means they must come from relatively nearby in the cosmic scheme of things, from within our local supercluster of galaxies. So which nearby monsters are responsible, and what specific cataclysmic event within them can launch such unbelievable projectiles? The hunt for the specific assassins continues. Even the darkest abyss in the universe possesses a hidden order, a measure of its deepest secrets. This is the mystery of black hole entropy, a concept that shatters our classical intuition. In the everyday world, entropy is a measure of disorder, and for any normal object like a box of gas, its entropy is proportional to its volume. The more space inside, the more ways the atoms can be arranged. But for a black hole, this rule is turned completely upside down. Its entropy is not tied to the vast, unknowable volume within. Instead, it is directly proportional to the surface area of its event horizon. The larger the black hole's surface area, the greater its entropy. This bizarre fact, first proposed by physicist Jacob Bekenstein, suggests that all the information about everything a black hole has ever consumed is not lost in its depths. It is painted like a cosmic fresco onto the two-dimensional boundary of its event horizon. Think of it as the universe's ultimate data storage system. The entropy of a black hole is astronomically large, a number so vast it counts every possible microscopic configuration, every single way the fundamental bits of information about its contents could be arranged on that spherical surface. This statistical interpretation means that a black hole with a specific mass, charge, and spin does not represent one single state, but a staggering number of microstates, each a different possible history of what fell in, all resulting in the same dark, smooth sphere we observe from the outside. Stephen Hawking initially resisted this idea as it seemed to violate thermodynamic principles, but his own discovery of Hawking radiation forced a profound reconciliation. If a black hole has entropy and a temperature, it must be a true thermodynamic object subject to the same laws as everything else. This revelation wove together gravity, quantum mechanics, and thermodynamics into a single, breathtaking tapestry. It directly fuels the holographic principle, the radical idea that our three-dimensional reality, with all its richness and depth, might be a projection from a two-dimensional surface at its boundary. The event horizon becomes a cosmic hard drive, storing information in Planck-sized pixels, the smallest possible units of area in the universe. The quest to understand this deep connection between entropy, information, and the nature of spacetime is now a central path in the search for a theory of quantum gravity. It suggests that the true nature of reality is not what we see in the volume around us, but in the information encoded on the surfaces that contain us, a secret written not in the darkness of the void, but on its shimmering, two-dimensional edge. These magnetic fields born from chaos can impose a stunning cosmic order. The swirling plasma of an accretion disk is a perfect engine for amplifying magnetic forces, thanks to a process known as the magnetorotational instability. Imagine a simple disk of gas where the inner material orbits faster than the outer material. Any weak magnetic field threading through this gas becomes stretched and twisted by the differential rotation, like taffy being pulled in two directions at once. This twisting action amplifies the magnetic field exponentially, transforming a faint whisper into a roaring, organized force. These strengthened magnetic fields then perform a crucial job, acting as the primary source of friction within the disk. They lock the gas together, creating a magnetic grip that allows the inner material to slow down and spiral inward toward the event horizon, while transferring its angular momentum outward. Without this magnetic mediation, the disk would be a placid, frictionless ring, and the black hole would starve. We can now directly witness this invisible architecture. The polarized light captured by the Event Horizon Telescope in the ring around M87's black hole is not random. It is a cosmic compass, its alignment revealing the precise structure of the magnetic field lines at the very precipice of the void. This polarized emission shows the fields are not tangled and chaotic, but remarkably ordered, coiled into a powerful spring capable of launching the galaxy-spanning jets we observe. This magnetic influence does not remain confined to the central engine. The powerful outflows and winds driven by the black hole act as a delivery system, carrying these amplified magnetic fields out into the galactic halo. The relativistic jets in particular are like magnetic freight trains, transporting ordered fields hundreds of thousands of light years into intergalactic space. As these outflows expand, they can drape the entire galaxy in a vast, coherent magnetic web. This has profound consequences far from the center. The presence of these large-scale magnetic fields in the halo influences how gas clouds collide and collapse. They provide a scaffolding that can either support gas against gravitational collapse or channel flows to trigger new star formation in specific regions. They can also suppress the birth of stars by adding magnetic pressure that prevents dense clumps from forming, effectively regulating the galaxy's growth from the inside out. The black hole, through its magnetic might, becomes a galactic architect, its invisible fields woven through the entire system, shaping its destiny from the core to the furthest reaches of its halo. A singularity without its event horizon would be the ultimate cosmic rule-breaker. This theoretical phantom is known as a naked singularity, a point of infinite density exposed to the rest of the universe, no longer cloaked by the protective veil of a black hole's event horizon. Its existence would tear apart a fundamental principle in physics called the cosmic censorship hypothesis. This idea, proposed by Roger Penrose, suggests that nature abhors such a sight and always wraps its singularities in an event horizon, protecting the universe from the unpredictable chaos that an exposed one would unleash. Without that dark shield, the laws of physics as we know them would break down in plain view. The consequences are staggering. A naked singularity would not be bound by the orderly predictions of general relativity. Its gravitational field could become so warped that it might create closed time-like curves, theoretical pathways that loop back on themselves. This is the realm of time travel paradoxes where cause and effect could become untangled. You could potentially travel back and encounter your past self, creating logical impossibilities that our understanding of reality cannot accommodate. How could such an object ever form? One possibility lies in the specifics of a collapse. If a massive star or a cloud of matter collapses with a very specific, rapid rotation or an unusual distribution of charge, it might theoretically collapse directly into a naked singularity, skipping the formation of an event horizon entirely. The mathematics of higher dimensional theories, like string theory, also allow for such exotic objects, suggesting they might exist in realms beyond our familiar 3 dimensions of space. The hunt to confirm or rule them out is a major endeavor in theoretical physics. If they do not exist, it validates cosmic censorship and reinforces the universe's preference for order. But if a single naked singularity were ever found, it would force a complete rewrite of Einstein's theory of gravity. Astronomers search for their signatures in the bursts of radiation from collapsing stars or in the precise shadows of distant gravitational lenses, looking for any anomaly that cannot be explained by a well-behaved black hole. So far, every observation aligns with the presence of a proper event horizon, but the search continues for that one cosmic rebel that could shatter our understanding of spacetime itself. The faint afterglow of creation holds secrets from the universe's first monsters. This is the cosmic microwave background, the oldest light we can see, a snapshot of the cosmos when it was just 380,000 years old. It appears as a nearly uniform veil of microwave radiation in every direction we look, a relic from a time before stars or galaxies existed. But this background is not perfectly smooth. It contains tiny temperature fluctuations, anisotropies, that are the blueprints for all future cosmic structure. Supermassive black holes, shining as the first brilliant quasars, may have left their own subtle scars on this primordial canvas. In the first billion years, these voracious black holes flooded the infant universe with intense ultraviolet radiation and powerful X-rays. This energy did not just clear the cosmic fog of neutral hydrogen during reionization. It could have also heated the sparse gas permeating the cosmos, causing subtle shifts in the CMB's temperature and polarization patterns. When high-energy photons from early quasars interacted with the cosmic microwave background, they could have imparted extra energy through a process called the Sunyaev-Zeldovich effect. This would create specific spectral distortions, tiny deviations from the perfect blackbody spectrum of the primordial light. It is like listening for a single, faint instrument that joined the cosmic symphony a moment after it began. The challenge is isolating this signal from the overwhelming primordial background. The imprints left by the first black holes are incredibly faint, buried under the signatures of later cosmic evolution. Astronomers must sift through exquisitely precise maps of the CMB, searching for statistical anomalies or specific polarization patterns that cannot be explained by the standard model of cosmology. Detecting even a hint of this would be a revolutionary discovery. It would provide direct evidence for when the first supermassive black holes switched on and how powerful they truly were. Their energy injection would be a fossil record of their feeding habits, telling us if they grew in sudden, violent bursts or through steady, sustained accretion. This would pin down their role in the epoch of reionization, the pivotal era when the universe transitioned from dark and opaque to transparent and filled with light. By reading these faint distortions, we could peer into the cosmic dawn and witness the moment the first giants awoke, their first breaths of energy permanently etched into the oldest light in the universe. The equations that describe a spinning black hole contain a hidden doorway to the past. Deep within the Kerr metric, a solution to Einstein's equations for a rotating black hole, lies a theoretical pathway called a closed time-like curve. This is not a machine with dials and levers, but a loop in the fabric of spacetime itself, created by the black hole's intense spin dragging reality into a vortex. If you could follow such a curve, you would find yourself traveling back to a moment in your own past, a possibility that shatters our everyday understanding of cause and effect. The gateway to this bizarre realm is the ergosphere, that region just outside the event horizon where space is dragged around faster than light. Under these extreme conditions, the mathematics suggests that such temporal loops could form, offering a cosmic shortcut not through space but through time. The paradoxes this creates are immediate and profound. What would happen if you went back and prevented your own birth? The universe would be faced with a logical contradiction it cannot resolve, a violation of the very principle of causality that underpins all of physics. To avoid these paradoxes, most physicists believe a powerful law, the chronology protection conjecture, must exist. Proposed by Stephen Hawking, it suggests that the laws of quantum physics would conspire to prevent closed time-like curves from ever forming in reality. The vacuum of space would become unstable, building up infinite energy that would destroy the time loop before it could be used. This is not the only theoretical hurdle. The most famous potential time machine, the wormhole, faces its own physical impossibilities. A wormhole, or Einstein-Rosen bridge, is a tunnel connecting two distant points in spacetime. To be traversable, this tunnel would have to be propped open against the force of gravity that wants to crush it shut. The only way to do this, according to the equations, is with something called exotic matter. This is not merely antimatter, but a substance with negative energy density, something that exerts negative pressure and repels gravity itself. We have never observed such a material, and it is unclear if it can even exist in stable quantities. Without it, any wormhole would snap shut the instant anything tried to pass through, making it useless for travel. These speculative ideas, while likely impossible in practice, are far from useless. They force us to confront the deepest questions about the nature of time. In general relativity, time is not a universal river flowing at the same rate for everyone. It is a flexible dimension interwoven with space that can be stretched and warped by gravity and motion. A closed time-like curve is simply an extreme manifestation of this flexibility. By exploring where our theories break down, we learn what they are truly made of. The violent physics at the edge of a spinning black hole acts as a cosmic firewall, not of heat but of logic, protecting the timeline from contradictions and preserving the orderly flow from cause to effect that our universe requires to exist. The smooth, dark surface of a black hole may hide a secret identity. Classical physics gives us the elegant yet unsettling no-hair theorem. This idea suggests that black holes are the ultimate simpletons of the cosmos. No matter how complex the star, planet, or astronaut that falls in, the resulting black hole retains only three basic pieces of information: its mass, its electric charge, and its spin. Everything else, every intricate detail about what built it, is permanently erased, shaved away. A black hole, according to this theorem, has no hair, no distinguishing features beyond those three numbers. It is a perfect bald sphere or a spinning disk of darkness with all the rich history of its contents utterly lost. This simplicity is beautiful, but it creates a profound conflict with the quantum world, which insists that information can never be truly destroyed. If the no-hair theorem is correct, then black holes are the ultimate violators of a fundamental cosmic law. This contradiction has driven physicists to ask a radical question. Could black holes actually have hair, subtle quantum fuzz that records what fell in? The challenge is to find a form of hair that does not violate Einstein's theory of gravity, which demands that black holes be smooth and simple. One proposal involves fields from the universe at large. Imagine a black hole sitting in a region of space filled with a particular kind of quantum field. This external field could interact with the black hole's gravity in a way that leaves a faint imprint on its structure, a subtle distortion that acts like a head of hair, storing information about the environment. Another idea suggests that the event horizon itself might be fuzzed up by quantum effects, not a sharp boundary but a seething layer of complexity that encodes data. How can we possibly test such an abstract concept? The answer arrives with the final, fading whisper of a black hole merger. After two black holes collide and become one, the newborn object does not simply sit in silence. It vibrates, ringing like a struck bell. This phase is called the ring down. Just as a bell's shape determines the specific tones it produces, a black hole's unique properties, defined by its mass and spin, dictate the frequencies or modes of its gravitational wave ringdown. The no-hair theorem makes a precise prediction. All the ringdown modes should be perfectly consistent with each other, all deriving from the same mass and spin. If the black hole has no hair, its ring should be pure and harmonious. But if it possesses any other hidden properties, any quantum hair, the ring down would contain dissonant notes, overtones that do not fit the simple three-property model. The incredible precision of gravitational wave observatories like LIGO and Virgo is now beginning to listen for this cosmic dissonance. By analyzing the ring down signals from future mergers, scientists will perform a direct test. Does the black hole's ring match the pure tone of a bald object, or does it have the complex timbre of a hairy one? The implications stretch to the very foundation of physics. Finding evidence for black hole hair would be a monumental discovery. It would mean that information is not lost after all, but preserved in some way on or around the event horizon. This would resolve the information paradox and provide our first concrete clues about how to weave gravity and quantum mechanics into a single, unified theory of everything. The silent ring of a newborn black hole may hold the secret to the universe's deepest operating principles. This warping of space does far more than just trap light. It twists the very path that light travels, creating one of general relativity's most spectacular predictions. Gravitational lensing turns a black hole into a cosmic magnifying glass, one that distorts and multiplies the images of anything behind it. Picture a single, distant galaxy situated perfectly behind a supermassive black hole from our viewpoint. The black hole's immense gravity acts like a flawed lens, bending the galaxy's light around itself. Instead of seeing one galaxy, we would see multiple smeared copies of it, stretched into luminous arcs encircling the central darkness. In a perfect alignment, this creates an Einstein ring, a complete circle of light surrounding the black hole's shadow, a halo forged by distorted spacetime. These are not mere illusions, they are precise cosmic tools. By measuring the distortion of these background objects, astronomers can map the black hole's gravitational field with incredible accuracy, weighing it independently of the stars orbiting it. This provides a crucial test of Einstein's theory in the most extreme environment imaginable. But the distortion is not limited to light. Time itself becomes a casualty of this intense gravity. According to general relativity, time passes at different rates depending on the strength of the gravitational field. Near the event horizon of a supermassive black hole, where gravity is almost immeasurably strong, time slows down dramatically compared to the rest of the universe. Imagine a hypothetical spacecraft on a mission to orbit just outside the event horizon. The crew might experience the passage of a single hour, completing their observations and data collection. But for everyone else in the universe, for mission control back on Earth, thousands of years would have passed. They would return to a civilization utterly transformed, their loved ones long gone, their world unrecognizable. This time dilation is not science fiction. It is a measurable effect. The GPS satellites orbiting our own planet have to account for tiny time shifts caused by Earth's much weaker gravity, or their navigation would fail within minutes. Near a black hole, this effect is magnified to an unimaginable extreme. This creates a profound and isolating paradox. An observer watching the doomed spacecraft from a safe distance would see its clock ticking slower and slower, its image reddening and dimming as the light struggles to escape the gravitational well. The ship would appear to freeze in time, hovering eternally at the edge of the void, never quite crossing from the outside perspective. These bizarre distortions of light and time are not just theoretical curiosities. They are the definitive signatures of warped space-time, allowing us to probe the very nature of reality and confirm that the universe operates by rules far stranger than our everyday experience suggests. The profound mystery of black hole information finds a potential key in the spookiest phenomenon in all of physics: quantum entanglement, that strange connection where two particles can share a single fate across any distance, might be the invisible thread stitching together the fabric of spacetime itself. This radical idea is crystallized in the ER=EPR conjecture. It proposes a stunning equivalence between two seemingly unrelated concepts. ER refers to an Einstein-Rosen bridge, which is the formal name for a wormhole, a tunnel through spacetime. EPR stands for Einstein, Podolsky, and Rosen, the physicists who first highlighted the bizarre nature of quantum entanglement. The conjecture suggests that every pair of entangled particles is not just mysteriously linked, but is actually connected by a microscopic, non-traversable wormhole. They are not communicating faster than light. They are, in a geometric sense, already touching through a hidden shortcut in the universe. This idea emerged directly from the battle over the black hole information paradox and the holographic principle. If the information of a three-dimensional volume is encoded on its two-dimensional boundary, then entanglement must be the glue that links the surface description to the interior reality. The event horizon, in this view, is a tapestry of entangled quantum bits, and the space inside the black hole is built from those connections. This leads to a profound and disturbing thought experiment known as the MPS firewall. Imagine an old black hole that has been evaporating for a long time via Hawking radiation. The paradox states that for information to be preserved, a late particle of Hawking radiation emitted today must be entangled with an early particle emitted long ago. But quantum mechanics also demands that this late particle must be entangled with its partner that fell into the black hole. A fundamental rule of quantum mechanics, monogamy of entanglement, forbids a particle from being fully entangled with two different systems at once. This creates a terrible choice. To save information, we must break a quantum rule. To save the quantum rule, we must accept that information is lost. The firewall proposal offers a brutal solution. The contradiction is so severe that it forces a break in the smooth fabric of spacetime at the event horizon. The entanglement between the inside and outside is severed, creating a wall of blazing energy that would instantly incinerate anything crossing it. While unsettling, this paradox is not a dead end. It is a powerful tool that uses entanglement to probe the very nature of the black hole interior, forcing physicists to refine their ideas about how quantum information and gravity intertwine. These are not just abstract puzzles for theorists. They are now driving real-world experiments in quantum gravity and quantum information theory. Laboratories are building tabletop analog systems using ultra-cold atoms or complex networks of lasers to simulate the dynamics of an event horizon and its entangled states. By studying how information scrambles and spreads in these controlled quantum systems, researchers can test the principles that may govern the most extreme objects in the cosmos. This is the ultimate bridge, connecting the behavior of a handful of atoms in a lab to the fate of a supermassive black hole at a galactic center, revealing that the rules of the very small might secretly orchestrate the destiny of the very large. The chaotic violence surrounding a black hole is a cosmic forge. Within the incredible temperatures and pressures of its accretion disk, a special kind of nuclear fusion can occur, one far more potent than the processes inside stars. This is black hole nucleosynthesis, and it forges the heaviest elements in the universe. In the furious whirlpool of superheated plasma, atomic nuclei collide with unimaginable force. They are not just fusing hydrogen into helium as in a star. They are undergoing rapid neutron capture, a process where atomic nuclei are bombarded by a dense soup of free neutrons, allowing them to build elements like gold, platinum, and uranium in a single, frantic burst. The black hole's environment is one of the few places with the extreme conditions necessary for this rapid creation. These newly forged elements do not remain trapped near the event horizon. They are launched back into the galaxy by the very outflows that regulate its growth. The powerful jets and winds act as a cosmic delivery system, carrying this enriched material hundreds of thousands of light years away. They seed the interstellar medium, the raw gas between stars, with the building blocks for rocky planets and ultimately life. We can see the chemical signature of this past activity imprinted on galaxies today. Astronomers measure metallicity, the abundance of elements heavier than hydrogen and helium across a galaxy's disk. Many show a distinct gradient with higher metallicity near the core that gradually decreases toward the outer edges. This gradient is a fossil record. It suggests that the galactic center was once a far more active and violent place, where a supermassive black hole in its active quasar phase cooked and then blasted heavy elements throughout its home. This process ties the black hole directly into the great cycle of cosmic matter. A massive star lives its life, fusing hydrogen and helium in its core before exploding as a supernova, scattering the first heavy elements into space. That enriched gas may eventually fall into the galactic center, fueling the black hole. The black hole then takes that stellar material and, in its own maelstrom, transmutes it into even heavier elements, launching them back out to form a new generation of stars and planets. The iron in your blood, the calcium in your bones, and the gold in a wedding ring were all created in the death throes of stars, but some of the very heaviest atoms were likely forged in the terrifying furnaces that rage at the edge of oblivion. Even the most predictable giants can suddenly flicker. These are black hole glitches, abrupt and mysterious changes in the light pouring from the galactic center. A black hole that has been quiet for years might suddenly flare, its brightness soaring in X-rays or infrared for a few hours before fading back into obscurity. At other times, its steady glow might abruptly dim, as if a cosmic hand passed briefly in front of a lamp. These are not random errors in our instruments. They are real events, sudden hiccups in the black hole's engine that betray the violent and dynamic processes churning just outside the event horizon. One of the primary suspects for these glitches is a sudden instability within the accretion disk itself. This vast, swirling river of gas is not perfectly smooth. Dense clumps can form, like lumps in a cosmic batter, orbiting the void. When one of these clumps finally loses its battle with gravity and plunges inward, it is torn apart in a final, violent burst of energy. We see this as a bright flare, a quick spike of light as the lump of gas is shredded and consumed. Another powerful trigger is a magnetic reconnection event. The incredibly powerful magnetic fields woven through the accretion disk are not static. They can become twisted and strained, storing energy like a wound-up spring. When the tension becomes too great, the field lines suddenly snap and reconfigure themselves in a more stable arrangement. This explosive reconnection releases a colossal amount of stored energy, accelerating particles to near light speed and creating a brilliant flash across the electromagnetic spectrum. It is a cosmic short circuit, a magnetic storm on a scale we can barely fathom. Sometimes the glitch is caused by something more substantial than a gas cloud. A small body, like an asteroid or a minor planet, straying too close can be the culprit. The black hole's immense tidal forces stretch and compress the object, heating it to incandescence before ripping it apart in a miniature version of a star's tidal disruption. This creates a distinct, short-lived flare, a quick snack for the monster that briefly illuminates its presence. Our own galactic center, Sagittarius A star, has become the perfect laboratory for studying these glitches. For years, it was a quiet and predictable neighbor, but recently it has become far more active. In May 2019, it produced an unprecedented infrared flare, becoming 75 times brighter than its normal state in just a few hours. This was not a gradual brightening, it was a sudden, explosive event, a dramatic glitch that captured the attention of astronomers worldwide. By monitoring Sagittarius A star with telescopes sensitive to every kind of light, from radio waves to gamma rays, scientists can piece together the cause of each flicker. A flare that appears simultaneously in infrared and X-rays points to a sudden heating event, like a magnetic reconnection. A burst that appears in one wavelength but not another might be the signature of a specific type of particle acceleration. Each glitch is a unique fingerprint, a brief window into the chaotic physics of the inner accretion disk and the powerful magnetic fields that control it. By watching the monster at our galaxy's heart twitch and flare, we are learning how its engine truly operates, moment by unpredictable moment. Their silent growth may be secretly fueling the universe's runaway expansion. This speculative idea places supermassive black holes at the heart of cosmology's greatest mystery, dark energy. For decades, we have known the cosmos is not just expanding but accelerating, pushed apart by an unknown force. The leading candidate is a constant energy intrinsic to the vacuum of space itself. But what if this energy is not a feature of empty space, but a consequence of its most massive occupants? One provocative theory suggests that the vacuum energy inside black holes could be contributing to this cosmic push. As black holes grow, their immense interior volumes, regions of spacetime disconnected from our own, might contain a form of energy that influences the universe on the largest scales. Every supermassive black hole, in this view, acts as a tiny engine of repulsion, and their collective growth over cosmic time adds up to the accelerated expansion we observe. Another compelling model directly links black hole growth to the universe's acceleration. In this scenario, the energy required to create a black hole's intense gravitational field, to warp spacetime into a closed surface, must be balanced by a corresponding negative energy in the cosmological background. As black holes gain mass through accretion and mergers, this balancing act requires the universe itself to compensate, potentially driving an accelerated expansion. It is as if the cosmos is stretching to accommodate the growing weight of its darkest giants. Testing these ideas is incredibly difficult. We cannot peer inside a black hole to measure its vacuum energy, and the effect of any single black hole is vanishingly small. The evidence must come from statistics, from observing the population of black holes across cosmic history. If their growth is truly coupled to dark energy, then the rate at which supermassive black holes gained mass over billions of years should mirror the era when the universe's expansion began to accelerate. Astronomers are now scouring ancient quasar light and counting black hole mergers across time, looking for this precise correlation. The challenge is untangling this signal from all the other processes that make black holes grow. Did they bulk up primarily during periods of intense galaxy collisions, or was their growth more steady, perhaps linked to the smooth infusion of dark energy? The answer is written in the fossil record of their masses, a record we are only now learning to read. This connection, if proven, would weave black holes into the ultimate fate of the cosmos. In a universe dominated by dark energy, the acceleration will continue indefinitely. Galaxies will be torn apart, and the cosmos will become a cold, expanding void. If supermassive black holes are the source, then their own growth sealed this destiny. They would be the architects of the cosmic end, their silent feasting in the galactic center ultimately determining the fate of everything. If black holes are the ultimate cosmic drains, what would their opposite look like? The equations of general relativity are beautifully symmetrical, and they allow for a hypothetical mirror image of a black hole known as a white hole. Where a black hole's event horizon is a one-way entrance, a white hole's boundary would be a one-way exit. Nothing from our universe could ever cross in, but matter and energy could potentially erupt from it in a continuous, violent outburst. It would be a cosmic fountain of infinite energy, a source rather than a sink. Another exotic alternative is the gravistar or gravitational vacuum star. This theoretical object avoids the problematic singularity entirely. Instead of a point of infinite density, a gravistar would contain a core of exotic dark energy, repelling gravity and preventing total collapse. This core would be encased in a shell of ultra-dense, ordinary matter, so thick and compact that it would mimic the appearance of a black hole's event horizon from the outside. These ideas are not just mathematical curiosities. They challenge our understanding of what a supermassive object at a galactic center could truly be. Could the dark giants we observe actually be gravistars, hiding a universe of exotic physics within their apparent boundaries? The primary problem with white holes is their profound instability within classical physics. A white hole would be the ultimate cosmic free lunch, a source of energy with no apparent cause. If one were to form, even a single photon falling onto its event horizon would be enough to collapse the entire structure, transforming it instantly into a black hole. They are considered mathematically possible but physically unrealistic in our universe's current state. However, the perspective shifts when we introduce quantum gravity. Some theories suggest that a black hole, after it has completely evaporated via Hawking radiation, might not vanish entirely. Its final moment could be a quantum bounce, a transition that transforms it into a white hole, briefly releasing all the information it ever consumed back into the cosmos. In this scenario, every black hole could have a white hole as its final state, a fleeting cosmic rebirth on timescales too vast to comprehend. The search for evidence now turns to the most energetic events in the sky. Could a particularly inexplicable gamma ray burst be the signature of a white hole briefly flashing into existence? Might the gravitational waves from a merging black hole contain subtle echoes, a faint ringing that a traditional event horizon would suppress but a gravistar's solid surface would produce? While no confirmed detection exists, each anomalous signal pushes us to consider the full spectrum of possibilities. These exotic objects are the ultimate thought experiments, forcing us to ask if the monsters we see are indeed the simple, dark pits we believe them to be, or if they are gateways to something far stranger, governed by laws we have only begun to imagine. The origin of the universe's largest structures might be written in the behavior of its smallest. To understand the supermassive black holes we see today, we must journey back to the universe's first fraction of a second, to an era of exponential growth known as cosmic inflation. This was not the slow, steady expansion we observe now, but a violent, faster-than-light stretching of spacetime itself that smoothed and flattened the infant cosmos. The seeds for everything from galaxies to black holes were sown in the quantum fluctuations that were magnified to cosmic proportions during this inflationary burst. Some of the most compelling theories now suggest a deep, fundamental link between this primordial event and the creation of the first black holes. In certain models, the same density fluctuations that gave rise to galaxies could have been intense enough to collapse directly into primordial black holes. These would not form from dying stars, but from the raw gravitational collapse of overdense regions in the early universe, providing the massive seeds needed to explain the rapid growth of supermassive black holes. Another, more exotic idea ventures into the realm of higher dimensions. It proposes that the fundamental objects driving inflation were not fields in the traditional sense, but black hole-like entities existing in a universe with more than 3 spatial dimensions. In this brain-world scenario, our entire cosmos could be a 3-dimensional membrane floating in a higher dimensional bulk. Collisions between our brain and others could have triggered inflation, with the energy of the impact creating black holes that were then projected into our lower dimensional reality. These concepts are not untestable philosophy. They leave distinct imprints on the oldest light we can see, the cosmic microwave background. The precise patterns of temperature variations in this afterglow are a fossil record of the initial conditions. If primordial black holes were abundant in the early universe, their collective gravitational influence would have subtly altered the way matter clumped together, leaving a specific signature in the large-scale structure of galaxies we map today. The fact that we do not see overwhelming evidence for this in our current data places strict limits on how many such black holes could have existed, narrowing down the possible models for their formation. This search is fundamentally a quest to understand the Planck epoch, the very first moment of time where our current laws of physics completely break down. It is a regime where gravity and quantum mechanics must finally unite. By studying the descendants of that era, the supermassive black holes at galactic centers, we are using them as telescopes to peer back into the initial conditions of everything. Their existence, their masses, and their distribution are cosmic clues, helping us piece together the physics of the universe's most violent and mysterious birth. A deep, rhythmic pulse beats across the cosmos, a coordinated signal from hearts of darkness separated by light years. The mystery of black hole synchronization suggests these titans can fall into a shared cadence, their feeding frenzies and explosive jets firing in an eerie cosmic harmony. This is not a random occurrence. When 2 supermassive black holes are locked in a binary dance, their gravitational fields intertwine, creating a complex web of influence that can orchestrate the flow of gas onto both of them. A shared reservoir of gas, a vast cloud enveloping the binary system, can be tugged and shaped by their dual gravity, falling onto one black hole and then the other in a regular, alternating sequence. This creates a predictable clockwork pattern of brightening and dimming, a lighthouse effect on a galactic scale. We see the evidence in the light curves of distant quasars, where X-ray and optical emissions flicker with a precise periodicity that can last for years, even decades. In some stunning cases, astronomers have observed 2 distinct active nuclei within a single merging galaxy, their flares rising and falling in tandem, as if connected by an invisible thread. The mechanism could be a direct gravitational nudge. As one black hole in the binary passes through a dense part of its companion's accretion disk, it can trigger a sudden surge of material falling inward, igniting a flare. The same gravitational perturbation can also funnel gas toward its own event horizon, creating a correlated outburst. Another possibility involves their powerful jets. If the jets from one black hole slam into the accretion disk of its partner, the immense energy transfer can heat the gas, causing it to glow brightly and initiate a new round of accretion, setting off a chain reaction of synchronized activity. This coordinated behavior offers a profound insight into the final stages of a galactic merger. Observing these synchronized systems allows us to map the orbital dynamics of the black hole binary itself. The period of the flickering gives us the orbital period, and the intensity of the flares reveals the amount of gas available in their shared environment. It shows us that these monsters do not exist in isolation. Even during their long, slow spiral toward a cataclysmic merger, their fates are linked not just by gravity, but by the very material they consume, a forced cooperation in the midst of a violent cosmic dance. What other secrets of their final union are written in these synchronized flashes of light, a secret code broadcast from the heart of colliding galaxies? The same forces that create solar flares on our sun operate on a truly galactic scale. A supermassive black hole generates a form of cosmic climate so vast it governs the weather for entire galaxies. This is not the gentle breeze of a solar wind, but a hurricane of radiation and high-energy particles screaming from its relativistic jets and powerful outflows. These jets act as colossal particle accelerators, flooding galactic space with X-rays and gamma rays, creating a pervasive and lethal radiation field. This high-energy environment can ionize vast clouds of gas, stripping electrons from atoms and preventing them from cooling to form new stars. For any planetary system lying in the path of these jets, the consequences are apocalyptic. The radiation would violently strip away atmospheres, sterilizing surfaces and scouring any potential for life. It is a celestial storm of unimaginable ferocity, one that can define the habitable zones of an entire galaxy, rendering vast regions utterly uninhabitable. Beyond the focused fury of the jets, a more subtle but equally powerful weather pattern emerges. This is the active galactic nucleus wind, a vast, spherical outflow of gas blown from the accretion disk by the intense radiation pressure of the black hole's feast. Think of it as a superheated hurricane wind flowing outward in all directions, not just from the poles. This wind can reach speeds of millions of miles per hour, and it carries enough force to sweep an entire galaxy clean of its star-forming fuel. Wherever this wind blows, it rams into dense molecular clouds, the very cradles of star birth. The impact heats and disperses the gas, preventing it from collapsing into new stars. This is how a black hole enforces a galactic drought, using its own energetic output to quench star formation and put its home galaxy on a path to a quiet, aging retirement. The entire galaxy exists within the black hole's weather system, its future climate controlled by the storm raging at its dark, silent heart. The violent weather of a galactic core forces a profound question about our own existence. Could the supermassive black hole at the heart of every galaxy be the ultimate arbiter of life itself? Its influence stretches far beyond star formation, potentially creating and destroying the very conditions needed for biology to arise. In a single cataclysmic outburst, an active galactic nucleus can flood its galaxy with sterilizing radiation, a wave of X-rays and gamma rays that would scour planets clean across thousands of light years. This resets the cosmic clock for life, wiping the slate clean in entire spiral arms and ensuring that any new beginnings start from scratch. Such an event is a galactic-scale extinction, a reminder that the universe can be a brutally inhospitable place. Yet, paradoxically, this same violence might also be a creator. The powerful shock waves from these outbursts can slam into quiet molecular clouds, compressing them and triggering the birth of new stars and their planetary systems. Our own solar system may have formed from the debris of such a cosmic detonation, its heavy elements forged in the death of earlier stars that were themselves influenced by the black hole's ancient cycles. The black hole, in its ferocious feedback, does not just suppress life, it also sows the seeds for its potential return. This leads to a startling possibility. Could life ever exist in the terrifying environment of the galactic center itself? It seems impossible, a realm bathed in relentless radiation and torn by gravitational tides. But life is tenacious, deep within the shielded cores of moons orbiting gas giants, or in the subterranean oceans of planets buried under thick, protective ice, organisms might persist. These would be worlds of permanent twilight, their surfaces lethal, but their interiors warmed by tidal forces from the black hole's immense gravity, creating isolated pockets of habitability in the most extreme neighborhood imaginable. This brings us to a haunting anthropic thought. Our quiet position in the galactic suburbs, far from the brilliant core, may not be a coincidence. We live in a region where the black hole's influence is gentle, its outbursts a distant memory. Is this the reason we are here to ponder it? If the inner galaxy were consistently calm, it might be filled with ancient, advanced life, but it is not. The supermassive black hole ensures that the galactic downtown is a dangerous, ever-changing landscape, perhaps making the quiet outskirts, like our own, the most likely addresses for life to gain a fragile foothold and survive long enough to look up and wonder. Their reign will last longer than all the stars combined, but even these cosmic emperors are not eternal. In the far, far future, when the last star has flickered out and the cosmos has grown cold and dark, the supermassive black holes will remain as the final monuments to a vanished age of light. Their eventual fate is tied to that faint quantum whisper we explored earlier, Hawking radiation. Isolated in the expanding void with no new gas to consume, they will slowly, inexorably begin to lose mass. The process is agonizingly slow, a cosmic drip of evaporation where the largest black holes could take a googol of years to vanish. That is a 1 followed by 100 zeros, a timescale so vast it makes the current age of the universe seem like a single blink. During this inconceivable era, these fading giants will become the universe's only beacons. In the profound blackness of a dead cosmos, the final light show will not be from new stars, but from the death throes of evaporating black holes. As they shrink, their temperature rises and the rate of evaporation accelerates. The final moments of a supermassive black hole would be a spectacular, violent burst of high-energy particles and radiation, a final shout in the eternal silence. This ultimate evaporation forces us to confront the deepest philosophical questions. What happens to all the information locked inside? Is it truly released back into the universe, as some theories suggest, or is it lost forever? The entire history of a galaxy, every star that fell in, every planet consumed, could be encoded in that final flash, and then nothing. In the heat-death scenario, the universe reaches a state of maximum entropy, a uniform, lukewarm sea of particles and radiation where no structure can form and no work can be done. With the black holes gone, the last organized structures in the cosmos have dissolved. Time itself may become meaningless with no events to mark its passage. The supermassive black holes, which once orchestrated the birth of galaxies and the flow of cosmic evolution, will have left behind only a cold, dark, and silent legacy, a universe that has run its course and returned to a state of perfect, featureless equilibrium. This final era is a battle of titans, a slow-motion war between gravity and the phantom force of dark energy. As the universe expands at an ever-increasing rate, the cosmic fabric stretches, pulling galaxies apart until each supermassive black hole is left utterly alone in an unimaginable void. The faint glow of the cosmic microwave background, the last echo of the Big Bang, will have redshifted into oblivion, leaving behind a darkness deeper than any we can conceive. Isolated and starving, these last giants have nothing left to consume but the vacuum itself. Their only remaining companions are the faint, random particles produced by Hawking radiation, a quantum drip that will slowly, over eons that dwarf the current age of the cosmos, drain their immense mass away. Yet even in this profound isolation, there may be one last burst of sound before the silence. The final supermassive black holes, wandering the dark for googles of years, might still find each other. Drawn together by their immense gravity across the expanding emptiness, they could merge in a last, thunderous collision. These would be the final gravitational wave bursts, the last notes in the cosmic symphony, rippling through a universe too cold and empty for any ear to hear them. As they evaporate, their final moments are not a quiet fade. Each one ends its life in a violent flash of high-energy radiation, a final, brilliant shout that for an instant outshines the dead cosmos around it. This is where physics meets its ultimate limits and speculation takes over. Could the information and energy released in that final flash be recycled? Some theories suggest that the conditions inside a black hole's last moments are so extreme that they could trigger the birth of a new universe, a cosmic seed sprouting in the barren soil of the old. Our entire cosmos might be the offspring of a black hole in a prior reality, part of an endless, branching tree of multiverses. In the near infinite time before the last black hole vanishes, another bizarre possibility emerges from the statistical churn of quantum fluctuations. A Boltzmann brain is a hypothetical, self-aware entity that could spontaneously form from random particle collisions in the void. It would be a conscious mind without a body, without a past, flickering into existence for just a moment with a full set of false memories, perhaps even remembering a life like yours before dissolving back into the chaos. It is a haunting thought that in the quadrillions of years of darkness, such phantoms might outnumber all the conscious beings who ever lived in the age of stars. This is the ultimate legacy of the supermassive black hole, from a seed in the cosmic dawn to a regulator of galaxies, and finally to a solitary monument in the dark. Its life cycle book ends the history of the universe. It begins in the fire of creation and ends as a potential source of a new one. The story of these cosmic giants is not just one of destruction, but of transformation, a testament to a universe where endings are woven into the fabric of beginnings and where the darkest objects may hold the secret to the next dawn. Our journey through 50 secrets reveals a universe sculpted by darkness. We have traveled from the birth of these giants in the primordial cosmos to their final, lonely evaporation in the distant future. We have seen them not as simple destroyers, but as cosmic regulators, architects of galaxies, and forgers of the very elements that build worlds and life. They control the birth of stars with their powerful feedback, enrich galaxies with heavy elements forged in their violent disks, and challenge our most fundamental laws of physics at their singularities. Every time you gaze at the starlight from a distant galaxy, you are witnessing the legacy of a supermassive black hole, an invisible hand that shaped its home into what it is today. These cosmic engines are the ultimate test of human curiosity, pushing us to look deeper and question further. If this exploration into the heart of darkness captivated you, show your support by liking this video and subscribing for more journeys into the mysteries of space. Let us know in the comments which secret reshaped your view of the cosmos the most. Thank you for joining this incredible voyage. Keep your eyes on the skies and